Please subscribe to support the channel. When we gaze up at the night sky, we see countless stars twinkling back at us, but hidden among them are true time travelers, objects so ancient that they connect us directly to the earliest chapters of the universe itself. Among these stellar relics, one stands out as a particularly remarkable find: Kepler 444. This star is not only fascinating because of its age, but because it represents something even more profound, a living fossil of our galaxy's infancy. Kepler 444 is extraordinary because it is estimated to be over 11 billion years old. To put that into perspective, our own Sun is about 4.6 billion years old, meaning Kepler 444 predates it by more than double. This makes Kepler 444 one of the oldest stars in the entire Milky Way galaxy known to harbor a planetary system. Think about that for a moment. This star was already shining brightly when the universe itself was still in its early stages of evolution, when galaxies were just beginning to take shape, and long before Earth or our solar system had even come into existence. The discovery of such an ancient star system immediately raises profound questions. How could planets form so early in the history of the universe, when the heavy elements that planets are made of were thought to be scarce? How have those planets managed to survive for billions upon billions of years, orbiting steadily around their parent star? And what might this mean for our search for life elsewhere in the cosmos? Kepler 444 pushes us to re-examine the very timelines we've constructed for cosmic history and planetary evolution. When scientists determined its age, they were astonished to find that Kepler 444 is nearly as old as the Milky Way itself. It is older than the Sun, older than Earth, older than most of the familiar stars in the night sky, and older than almost everything we can see in our local galactic neighborhood. It is not just another point of light in Lyra. It is a direct witness to nearly the entire history of the galaxy, surviving events and transformations that wiped out or reshaped countless other stellar systems. What also makes Kepler 444 particularly intriguing is the fact that it doesn't exist in isolation. It has a family of planets, 5 small rocky worlds circling tightly around it. The existence of these planets alongside such an ancient star sends shockwaves through our understanding of when and how planets form. Until Kepler 444 was studied, astronomers assumed that rocky planets like Earth required significant amounts of heavy elements to build. But here we have evidence that small, Earth-sized planets were forming when the universe was still relatively young. That means, in theory, rocky worlds like ours could have existed far earlier than we ever imagined. From a storytelling perspective, Kepler 444 is almost poetic. Imagine tracing the cosmic timeline backward. While Earth is just a young child at 4.5 billion years old, Kepler 444 is an elder, already middle-aged by the time Earth even took its first breath. While humans are only a blip on the cosmic scale, this star has been shining steadily for over 11 billion years, a silent guardian of secrets we are only now beginning to uncover. This star is not simply a scientific curiosity. It is a reminder of how small and fleeting our place is in the grand story of the cosmos. It challenges us to expand our perspective of time, to understand that entire planetary systems have come and gone, evolved and endured, long before Earth was even conceived. It whispers to us that the universe has always been capable of producing planets, perhaps even habitable ones, much earlier than we dared to dream. In short, Kepler 444 is more than just a star. It is a cosmic time capsule. It carries with it the story of ancient galaxy building, early planet formation, and the resilience of planetary systems over unimaginable spans of time. Its discovery was like unearthing a relic from a civilization long past, except this relic was born from the very fire of the universe itself. The Milky Way galaxy is our cosmic home, a sprawling collection of stars, planets, gas, dust, and dark matter arranged in a magnificent spiral form. When astronomers attempt to count the stars within it, the numbers quickly become staggering. Estimates range from 100 billion to over 400 billion stars. That means every patch of sky we look at is teeming with suns of all kinds. Blue giants burning out in mere millions of years, red dwarfs slowly glowing for trillions, and everything in between. Against this immense backdrop, each star has its own unique history, a timeline stretching across cosmic epochs. But among this vast sea of stellar light, only a tiny fraction of stars are as ancient as Kepler 444. To set the scene properly, imagine the galaxy itself as a kind of city, a sprawling metropolis of stars. Some stars are brand new, like gleaming skyscrapers just built yesterday, while others are ancient ruins, still standing despite the centuries. Kepler 444 is one of those ruins, a relic from a time when the city itself was still under construction. Most of the stars we see in the night sky today are relatively young compared to the universe's age, but Kepler 444 predates the majority of them by billions of years. This is important because the Milky Way did not spring into existence all at once. It grew slowly, over billions of years, through mergers with smaller galaxies, bursts of star formation, and recycling of stellar material. Stars like our Sun, for example, were born from multiple generations of cosmic evolution. When massive stars exploded long ago, they seeded space with heavy elements like carbon, oxygen, iron, and silicon, ingredients necessary for rocky planets and, eventually, for life. By the time our Sun formed 4.6 billion years ago, the galaxy was already enriched with these elements, making it relatively straightforward for Earth and its siblings to appear. But Kepler 444 came into existence much earlier, when the Milky Way was still in its youth, less chemically enriched and much more chaotic. Back then, the galaxy hadn't yet built up its spiral arms in the way we see them now. It was a rougher, more turbulent environment, where star formation was occurring rapidly but with far fewer resources. For a planetary system to emerge in such an early era is nothing short of astonishing. Out of the billions upon billions of stars, only a handful are confirmed to rival Kepler 444 in age. Astronomers often call these objects galactic fossils because they preserve the conditions of a time long gone. These ancient stars are typically found in the halo of the Milky Way, a roughly spherical cloud of stars that surrounds the galactic disk, or in ancient globular clusters, which are dense spherical collections of tens of thousands to millions of stars all born in the early days of the galaxy. However, Kepler 444 is different. It's not isolated in a halo or hidden in a globular cluster. It sits relatively nearby in the galactic disk itself, in the constellation Lyra. That means it survived in a region of the galaxy that has been heavily influenced by subsequent generations of star formation, supernova explosions, and galactic dynamics. Its survival there makes it even more unusual. Now, when we talk about billions of stars, it's easy for the mind to drift and lose a sense of scale. But consider this: if we were to count every star in the Milky Way, one per second, it would take you thousands of years to finish. In that unimaginable expanse of stellar diversity, the fact that astronomers can pinpoint and study one single star like Kepler 444, out of hundreds of billions, is almost miraculous. And not only did they find it, but they discovered it harbors 5 planets, which makes it even more extraordinary. What's particularly fascinating is that most stars that form planets do so much later in cosmic history, when there are more heavy elements available. Younger stars, like those in the Sun's stellar neighborhood, are richer in metals and thus more conducive to planet formation. Yet here we have a star from the dawn of the galaxy that managed to produce planets despite its low metallicity. That makes Kepler 444 not only rare in age, but also rare in what it represents about planetary formation. It tells us that the building blocks of worlds were being assembled far earlier than our traditional models suggested. If we zoom out further, the Milky Way itself is just one of 2 trillion galaxies in the observable universe. Each of those galaxies has its own mixture of ancient and young stars. By studying ancient stars like Kepler 444 in our own galaxy, astronomers are effectively peering into a time window that applies across the cosmos. The lessons learned here ripple outward, giving us insights into when and where planets, and potentially life, might have appeared throughout the universe. In short, while our galaxy is bursting with stars of every age and type, only a select few are as ancient as Kepler 444. That makes this star not just another point of light, but an exceptional treasure trove of information. It is one of the rare elders still burning steadily, reminding us that the galaxy has been active for nearly its entire history and that planet formation began astonishingly early. Understanding this context helps us grasp just how unique Kepler 444 is. Out of billions of stars in the Milky Way, and trillions more in the universe, this one ancient orange dwarf and its compact family of planets tell us a story that stretches back nearly to the beginning of time itself. That story is not just about astronomy, it is about survival, persistence, and the resilience of the cosmos. Kepler 444 may be ancient, but in the vast scale of the universe, it isn't all that far away from us. Its home lies within the familiar celestial territory of Lyra, a small but prominent constellation in the northern sky. For thousands of years, humans have looked up at Lyra, charting it in myths, stories, and star maps. Today, Lyra is most famous for containing Vega, one of the brightest stars in the sky, and also for hosting the famous ring nebula, M57. But tucked away in this constellation is something far less obvious, yet infinitely more remarkable: Kepler 444. The star sits at a distance of about 117 light-years from Earth. On the human scale, that seems unimaginably far. After all, 1 light-year is nearly 6 trillion miles. But in galactic terms, Kepler 444 is practically a next-door neighbor. The Milky Way's disk stretches about 100,000 light-years across, so a star that is only 117 light-years away is well within our local neighborhood of the galaxy. That proximity is what allows astronomers to study it in detail, using telescopes sensitive enough to pick up subtle vibrations and shifts in its starlight. To visualize its location, imagine the night sky on a clear summer evening in the northern hemisphere. High overhead, you can see Vega, the dazzling blue-white star that forms part of the summer triangle along with Altair and Deneb. Just a short hop away in the sky, hidden from unaided human eyes but visible to instruments, lies Kepler 444. Unlike Vega, which shines bright enough to be seen without a telescope, Kepler 444 is faint. It has an apparent magnitude of around 8.9, which means you'd need at least a small telescope or binoculars to glimpse it directly. Its faintness is due not to distance, since 117 light-years is relatively close, but to its nature as a K-type orange dwarf star, which naturally emits less light than a star like our Sun or a hot blue star like Vega. Lyra itself is a constellation steeped in human imagination. In Greek mythology, it represents the lyre, a harp-like musical instrument associated with the legendary musician Orpheus. According to the myth, after Orpheus's tragic death, Zeus placed his lyre in the heavens to honor him. For ancient skywatchers, Lyra was a symbol of art and harmony. Now, in a poetic twist, modern astronomy has revealed that this same region of sky is home to Kepler 444, a star that connects us not just to myths but to the very beginnings of galactic history. From Earth, astronomers use Lyra as a marker of sorts. It's a relatively small constellation, but because of Vega's brightness, it is easy to find. That makes it a convenient hunting ground for telescopes like NASA's Kepler Space Telescope, which surveyed a fixed patch of sky in Cygnus and Lyra during its mission. This is how Kepler 444 came into focus in the first place. Not because it stands out visually, but because its light flickered in just the right way to reveal the presence of orbiting planets. Even though Kepler 444 is faint to our eyes, its location makes it especially valuable for study. Many stars we learn about from exoplanet discoveries are far more distant, sometimes thousands of light-years away, which makes them harder to examine in detail. Kepler 444's relative closeness means scientists can measure its starlight with higher precision, analyze its composition, and detect the delicate oscillations that tell us its age. Its placement in Lyra also links it to one of the richest observational fields in modern astronomy, the very patch of sky that transformed our understanding of planets beyond the solar system. Another fascinating point about its location is that Kepler 444 is part of the galactic thick disk, an older stellar population that orbits the center of the Milky Way in a puffed-up, thicker distribution compared to the thin disk where younger stars like the Sun are found. Stars in the thick disk tend to be ancient and metal-poor, consistent with what scientists see in Kepler 444. This galactic context reinforces the idea that its neighborhood and orbital path are distinct from the one that nurtured our Sun billions of years later. So while Kepler 444 is a faint star invisible to casual stargazers, its position in Lyra, only 117 light-years away, makes it incredibly important to science. From that spot in the sky, it beams information to us that stretches back nearly the entire age of the galaxy. For astronomers, its location is like having a time machine parked right in our local neighborhood, waiting to be studied. The story of Kepler 444's discovery begins with one of NASA's most groundbreaking missions, the Kepler Space Telescope. Launched in March 2009, Kepler was designed to answer a deceptively simple question: how common are planets beyond our solar system? To find the answer, it focused its gaze on a single patch of the sky, watching more than 150,000 stars in the constellations Cygnus and Lyra. This small region, although just a fraction of the night sky, was chosen because it was dense with stars and away from the bright interference of the Milky Way's galactic plane. The telescope's method of discovery was ingenious. Rather than capturing images of planets directly, Kepler used the transit method, measuring the slight dimming of starlight that occurs when a planet crosses in front of its star, blocking a tiny fraction of the light. These dips in brightness are extremely subtle, often less than 1%, but Kepler's instruments were sensitive enough to detect them. By carefully recording these periodic flickers, astronomers could infer not only the presence of planets, but also their size, orbital period, and distance from their star. It was during this mission that Kepler 444 came into focus. Initially, it was just one star among many in Lyra, faint and unremarkable. But as Kepler gathered years of continuous data, astronomers noticed something extraordinary: 5 distinct sets of periodic dimmings, each corresponding to a planet. These planets, all smaller than Earth, orbited very close to their host star. In 2015, a team of scientists led by Tiago Campanti, an astrophysicist at the University of Birmingham, announced the discovery in the journal The Astrophysical Journal. What set Kepler 444 apart was not simply the presence of planets, but the age of the system. At first, astronomers assumed that a star with such low metallicity, meaning it lacked heavy elements like iron, magnesium, and silicon, would not be capable of forming planets. Previous models suggested that planetary systems required an abundance of these heavier elements, since they are the raw materials for rocky planets. But Kepler 444 defied those expectations. Not only did it have planets, it had 5 rocky ones, and they were orbiting a star that turned out to be more than 11 billion years old. This was not only surprising, it was paradigm-shifting. To determine that age, scientists used a powerful technique called astroseismology, which studies oscillations, or starquakes, within a star. Much like how geologists study seismic waves to understand Earth's interior, astronomers study these stellar vibrations to probe the inner structure of a star. Kepler's sensitive instruments detected tiny variations in Kepler 444's brightness caused by these oscillations. From this, scientists could calculate the star's size, density, and most importantly, its age with unprecedented accuracy. The announcement of Kepler 444 in 2015 made headlines around the world. It wasn't just another exoplanetary system. It was one of the oldest known planetary systems in the galaxy. This meant that planets like Earth were being formed when the universe was still in its adolescence, only a couple of billion years after the Big Bang. The implications were profound. If rocky planets were forming this early, then the potential for habitable worlds, and perhaps even life, might have arisen long before Earth itself existed. From the perspective of the Kepler mission, Kepler 444 was one of its crowning achievements. While Kepler discovered thousands of exoplanets, most of them were relatively young systems. Kepler 444 was unique in that it wasn't just about planets, but about cosmic history. It provided a window into an era when the galaxy was young, raw, and just beginning to create the structures we now see today. It is worth pausing to appreciate how remarkable this discovery was on a technical level. Kepler was not designed to find ancient stars. Its mission was to count planets and determine their frequency. Yet by combining the transit data with astroseismology, scientists could go far beyond the telescope's original mandate. They uncovered not only the planets but also their incredible antiquity. This is a testament to both the design of the mission and the ingenuity of the scientists analyzing the data. Since its discovery, Kepler 444 has become a touchstone in exoplanet science. It has been used in countless papers and discussions as evidence that planetary systems can survive for nearly the entire age of the galaxy. It has also become a benchmark for studying the relationship between stellar metallicity, planetary formation, and long-term system stability. For many astronomers, it remains one of the most exciting and humbling discoveries of the Kepler era. So, in 2015, what started as just another faint star in Lyra turned into something extraordinary. A time capsule from the early universe, holding within it the story of one of the oldest planetary systems ever discovered. Without the precision of the Kepler Space Telescope, and without the determination of astronomers to sift through massive amounts of data, Kepler 444 might have remained an anonymous speck of light in the night sky. Instead, it has become a symbol of how far our science has come, and how much farther we still have to go in unraveling the mysteries of the cosmos. Kepler 444's identity as a star is deeply tied to its classification. Astronomers categorize stars based on their spectral type, which is essentially a way of grouping stars by their temperature, color, and other physical properties. Kepler 444 belongs to a class known as K-type stars, sometimes referred to as orange dwarfs. This detail may sound simple, but it carries enormous significance for understanding the nature of the star, its planets, and why it has endured for such a staggering length of time. The classification system for stars is arranged in a sequence: O, B, A, F, G, K, and M, often remembered by the mnemonic "Oh be a fine girl guy, kiss me." At one end of the scale, O-type stars are blazing blue giants, incredibly hot, luminous, and short-lived. At the other end, M-type stars are cool, faint red dwarfs, which can live for trillions of years. Nestled between them are the intermediate categories, with our Sun falling into the G-type category. Kepler 444, as a K-type star, sits just cooler and smaller than the Sun, glowing with a steady orange light. To put numbers on it, Kepler 444's surface temperature is estimated to be around 4,700 Kelvin, compared to the Sun's 5,778 Kelvin. This cooler temperature gives it its orange hue, as opposed to the Sun's yellow-white appearance. In terms of size, Kepler 444 is also smaller, with about 75% the mass of the Sun and roughly 75% its radius. This reduction in size and temperature means that it emits less energy overall, shining more faintly than the Sun. That's why Kepler 444 is invisible to the naked eye despite being only 117 light-years away, while brighter stars like Vega in the same constellation dominate the night sky. One of the most critical implications of Kepler 444's classification as a K-type dwarf is its longevity. Stellar lifetimes depend on mass. The more massive the star, the faster it burns through its nuclear fuel. Massive stars might shine brilliantly, but they live for only a few million years before exploding in spectacular supernovae. In contrast, smaller stars like K-type and M-type dwarfs burn their hydrogen more slowly, allowing them to live for tens of billions, even up to a trillion, years. For Kepler 444, this means that it has already survived for over 11 billion years and still has billions more years ahead of it. In cosmic terms, it is both ancient and remarkably stable. This longevity has a profound effect on its planetary system. A star like Kepler 444 doesn't undergo the violent, short-lived evolution of massive stars, which can destabilize or destroy surrounding planets. Instead, it provides a consistent gravitational anchor and steady radiation environment over eons. The fact that its 5 planets have remained intact for such an immense span of time is a direct consequence of Kepler 444 being a modest, slow-burning K-type star. If it had been born as a massive O-type or B-type star, the entire system would have been obliterated billions of years ago. Another defining feature of K-type stars is that they are considered sweet spot stars for the potential of habitability. They are cooler and dimmer than G-type stars like the Sun, which means their habitable zones, regions where liquid water could exist on a planet's surface, are closer in. At the same time, they are more luminous and stable than M-type red dwarfs, which are notorious for violent stellar flares that can strip planetary atmospheres. This makes K-type dwarfs an attractive target in the search for life-bearing worlds. Unfortunately, in the case of Kepler 444, its planets all orbit much too close to the star, far inside any potential habitable zone. Still, the principle holds. If other K-type stars host planets at just the right distances, they could be ideal places for life. The classification of Kepler 444 also tells us something about its light and spectrum. When astronomers look at a star's spectrum, they see absorption lines, fingerprints of the elements present in its outer layers. For Kepler 444, these spectral signatures confirm not only its K-type status but also its metal pore composition. Unlike younger G-type stars like our Sun, which are rich in heavy elements, Kepler 444 has far fewer. This aligns perfectly with its age. It formed in an era of the galaxy when fewer heavy elements had been created by earlier generations of stars. It's fascinating to think about how this classification ties Kepler 444 into the bigger picture of stellar evolution. K-type stars are sometimes called Goldilocks stars because they combine longevity, stability, and relatively mild radiation output. If Kepler 444's planets had formed in its habitable zone instead of crowding close to the star, this system could, in theory, have supported life for billions of years longer than Earth has even existed. That tantalizing thought underscores how important stellar classification is, not just as a label, but as a key to understanding a star's past, present, and future potential. So, in summary, Kepler 444's identity as a K-type orange dwarf explains its smaller size, cooler temperature, orange glow, and, most importantly, its incredible longevity. This modest classification is the secret to its survival. It has endured across almost the entire history of the galaxy, holding its planetary system in orbit for longer than Earth has even been a concept. Its very nature ensures that it will continue to shine steadily for billions of years to come, a beacon of stability in a galaxy that has been anything but stable. Determining the age of a star is one of the most challenging tasks in astronomy. Unlike trees, stars don't grow rings that can be counted, and unlike rocks on Earth, they can't be sampled and dated directly. Instead, scientists must rely on indirect methods, interpreting the faint signatures hidden in starlight. For Kepler 444, astronomers employed one of the most powerful tools in modern astrophysics, astroseismology. This technique, which measures the subtle vibrations within a star, provided the key to unlocking its astonishing age, over 11 billion years. To understand how this works, imagine a star as a vast, resonant sphere of hot plasma. Just like musical instruments, stars can ring. Pressure waves travel through their interiors, causing the surface to oscillate ever so slightly. These oscillations are incredibly small, typically changing the star's brightness by just a few parts per million. To our eyes, the star looks perfectly steady. But with sensitive instruments like those aboard the Kepler Space Telescope, these variations can be measured with exquisite precision. Each oscillation mode corresponds to waves traveling through different layers of the star. By studying these vibrations, astronomers can infer properties like the star's density, internal structure, radius, and age. It's akin to how geologists use earthquakes to study Earth's interior, or how doctors use ultrasounds to look inside the human body. In fact, many scientists describe astroseismology as listening to the music of the stars. For Kepler 444, this technique was especially valuable. When its vibrations were analyzed, they revealed that the star was not only smaller and cooler than the Sun but also remarkably old. The oscillations showed a structure consistent with a star that had long since settled into stable hydrogen fusion in its core and was nearing the later stages of its main sequence life. By comparing the vibration patterns to stellar models, computer simulations that describe how stars evolve over time, scientists were able to pin down Kepler 444's age with surprising accuracy, 11.2 billion years, plus or minus about a billion. To appreciate the significance of this, consider how difficult stellar age determination normally is. For younger stars, astronomers often estimate ages based on how fast they rotate or how active their magnetic fields are. For older stars, those indicators become less reliable. But astroseismology bypasses these uncertainties, giving a direct probe into the star's internal physics. Without it, Kepler 444's age might have remained a mystery. This technique has been applied to many stars, but in the case of Kepler 444, the results were breathtaking. The data confirmed that this star formed when the Milky Way itself was still young, only a few billion years after the Big Bang. It is among the earliest generations of stars in our galaxy still shining today. Its ancient age also helps explain its low metallicity. When Kepler 444 was born, the galaxy hadn't yet produced many heavy elements. It is a snapshot of the universe at a time when the first galaxies were assembling, and stars like it were some of the earliest building blocks. Astroseismology doesn't just give a number for age, it gives context. For Kepler 444, it revealed that this star has been remarkably stable for billions of years. Unlike massive stars that live fast and die young, Kepler 444 has spent almost all of cosmic history in the same state it is in now, quietly fusing hydrogen into helium, glowing steadily in orange light. This stability is why its planetary system has endured without disruption for such an extraordinary span of time. The ability to measure a star's age so precisely is a triumph of modern science. Not long ago, astronomers could only guess at stellar ages within a broad range. Now, thanks to missions like Kepler, and to the refinement of astroseismology, we can listen to the vibrations of distant stars and determine when they were born. In the case of Kepler 444, that birth happened when the universe itself was still in its infancy, just 2.6 billion years after the Big Bang. Think about that. Earth is only 4.5 billion years old, yet Kepler 444 had already existed for more than 6 billion years before Earth even formed. Its oscillations, now measured by our instruments, carry within them the history of nearly the entire galaxy. They are a kind of cosmic heartbeat that has been pulsing steadily for over 11 billion years, and by decoding them, we gain a direct connection to the ancient universe. So, through astroseismology, astronomers didn't just measure vibrations, they opened a window into time itself. Kepler 444's age is not just a number. It is a story of resilience, of stability, and of survival across cosmic history. Without this technique, we might never have realized just how extraordinary this star and its planetary system truly are. When we talk about Kepler 444's age, 11.2 billion years, it's easy for the mind to gloss over the magnitude of that number. After all, billions of years stretch so far beyond human experience that they can feel abstract. But the real power of Kepler 444's story comes into focus when we compare its age to familiar reference points: our Sun, Earth, the Milky Way galaxy, and even the universe itself. Doing so makes the true significance of this star's antiquity much more tangible. Let's start with something close to home: the Sun. Our star is about 4.6 billion years old. That means Kepler 444 is more than twice as old as the Sun. To put that in perspective, imagine the Sun as a middle-aged adult, perhaps in its 40s. By that analogy, Kepler 444 would be a wise elder who had already lived a full life before the Sun was even born. In fact, when our solar system finally took shape, with Earth, Mars, Jupiter, and the other planets swirling into existence, Kepler 444 had already been shining for around 6.5 billion years. That's longer than Earth has even existed. Now consider Earth itself. Our planet formed 4.54 billion years ago, and life began to emerge not long after, perhaps within a few hundred million years. But Kepler 444 predates Earth's formation by more than an entire solar system's lifetime. It's sobering to think that while Kepler 444's planets had already been orbiting their star for eons, Earth was still just stardust scattered through the galaxy, waiting for gravity and chemistry to pull it together. By the time dinosaurs roamed our world some 200 million years ago, Kepler 444 had already experienced over 11 billion years of cosmic history. Then there's the Milky Way galaxy itself. Our galaxy is estimated to be around 13.6 billion years old, forming not long after the Big Bang. That makes Kepler 444 nearly as old as the galaxy itself. If the Milky Way were a human being, Kepler 444 would be among its very first generation of children, one of the original pioneers born in the galaxy's formative years. This gives Kepler 444 a special status. It is not just an old star, but an ancient witness to almost the entire lifespan of our galaxy. While countless stars have been born and died since then, Kepler 444 has persisted, glowing steadily in orange light as the Milky Way built itself into the magnificent spiral we see today. Now zooming out further, we compare it to the universe itself, which is about 13.8 billion years old. Kepler 444 formed just 2.6 billion years after the Big Bang. That's remarkably early. To put it in human terms, if the entire age of the universe were compressed into a single year, the Big Bang would occur at midnight on January 1st. Galaxies would begin to form in the first couple of months. In that cosmic calendar, Kepler 444 would have formed by early March, while Earth and the Sun wouldn't appear until sometime in September. Humanity wouldn't arrive until the very last seconds of December 31st. In this scale, Kepler 444 has been shining for nearly the entire year of cosmic history. This comparison paints a clear picture. Kepler 444 is not just older than Earth or the Sun, it is a survivor from the dawn of the galaxy. Its very existence demonstrates that stars and planets were forming in the universe's earliest eras, when heavy elements were scarce and galaxies were still young and turbulent. It reminds us that our solar system, often the center of our perspective, is in fact very young compared to the broader cosmic story. It also reframes how we think about the potential for life. Earth has hosted life for at least 3.5 billion years, and in that time, it has gone from simple microbes to a planet capable of reflecting on its own origins. But if stars like Kepler 444 formed planets so early, then life elsewhere in the universe could, in principle, have had a head start of billions of years compared to us. Civilizations, if they exist, might have been developing while Earth was still a molten rock. The age comparison between Kepler 444 and our Sun thus doesn't just highlight longevity, it stretches the imagination about what other cosmic histories might exist beyond our own. Finally, The age contrast underscores the fragility of our place in the universe. The Sun will last another 5 billion years before becoming a red giant and eventually fading into a white dwarf. Kepler 444, being smaller and more stable, will outlive the Sun by billions of years more. Long after Earth has been swallowed by the expanding Sun, Kepler 444 will still be glowing, quietly circling in Lyra with its compact family of planets. So, when we compare Kepler 444's age with that of the Sun, Earth, the Milky Way, and the universe itself, we begin to see just how special it is. It is an elder in every sense, nearly as old as the galaxy, twice the age of our solar system, and still steadfast after 11 billion years. Kepler 444 is not just a star, it is a time capsule, a living bridge to the earliest days of the cosmos. To truly appreciate the significance of Kepler 444, we need to step back from the scale of our solar system, even from the scale of our galaxy, and place it in the grand context of the universe itself. Astronomers estimate the universe to be about 13.8 billion years old, beginning with the Big Bang, a moment when space, time, matter, and energy all erupted into existence. In that searingly hot and dense first instant, the universe was nothing like what we see today. There were no stars, no galaxies, no planets, only a rapidly expanding soup of particles and radiation. Over time, that primordial fireball cooled. After about 380,000 years, the universe reached a point where atoms could form, mostly hydrogen and helium, with trace amounts of lithium. This was the moment of cosmic recombination, when the universe first became transparent, allowing light to travel freely. That light is what we detect today as the cosmic microwave background, the faint afterglow of the Big Bang. But even then, there were still no stars. The cosmos was a vast, dark sea of gas. It wasn't until hundreds of millions of years later that the first stars ignited. Gravity gathered gas into dense knots, sparking nuclear fusion and giving birth to the first stellar beacons. These early stars were massive, brilliant, and short-lived, burning out in just a few million years. When they exploded as supernovae, they seeded the universe with the first heavier elements: carbon, oxygen, iron, materials necessary for future generations of stars and planets. Galaxies began to assemble as these stars and their remnants coalesced into larger structures. Now, here's where Kepler 444 enters the story. This star formed only 2.6 billion years after the Big Bang. To put that in perspective, at that stage, the universe was still in its infancy. It had only just passed through its first era of galaxy building. Many of the galaxies we see today, including the Milky Way, were still forming, merging, and growing in complexity. In cosmic terms, 2.6 billion years might sound like a long time, but when measured against the universe's 13.8 billion year age, it's equivalent to the first fifth of cosmic history. Think of the universe's timeline as a 24-hour day. The Big Bang happens at midnight. By about 1 a.m., the first stars appear. By 2 or 3 a.m., the first galaxies form. Kepler 444 would have been born around 4 a.m., while our Sun wouldn't arrive until late afternoon. Close to 5 p.m. humanity wouldn't appear until the final seconds before midnight. That's how early Kepler 444 is, a true dawn-of-the-universe star. The fact that Kepler 444 formed this early is astounding because of what it implies about the conditions of the universe at the time. Heavy elements, which astronomers collectively call metals, were incredibly scarce back then. Most of the matter was still hydrogen and helium. According to older theories, this lack of metals would make planet formation extremely unlikely. Yet Kepler 444 managed to form 5 rocky planets despite the scarcity of raw materials. That tells us something crucial. The universe began producing planets much earlier than we once believed possible. Kepler 444 is not just a witness to cosmic history, it is part of the first wave of stars that could form planetary systems. It carries in its chemistry and structure the fingerprints of an ancient universe, one that looked very different from today's. When astronomers measure its low metallicity, they see confirmation of its ancient birth. It was assembled from material forged in just a few earlier generations of stars. This means that Kepler 444 and its planets are survivors from an era when the universe was still rough, chaotic, and very young. Placing Kepler 444 into this cosmic framework changes how we think about our own origins. Our Sun and Earth are relatively recent arrivals, forming just 4.6 billion years ago, long after the galaxy had matured and enriched itself with heavy elements. But Kepler 444 predates that by more than 6 billion years. Its very existence proves that the universe was already capable of building planetary systems while Earth was still billions of years away from forming. This raises profound questions. If rocky planets like those around Kepler 444 were forming only 2.6 billion years after the Big Bang, then potentially habitable worlds could have existed far earlier in cosmic history than we imagined. That means that if life ever arose on one of these early planets elsewhere in the universe, it could have had a head start of billions of years compared to life on Earth. Civilizations, if they ever emerged, might have flourished and vanished long before our planet even formed. Kepler 444, then, is not merely old, it is a cosmic pioneer. It belongs to one of the first generations of stars in the Milky Way's thick disk, forged in an era when the universe was still experimenting with the recipe for stars and planets. Its light is a messenger from a time when the cosmos was still new, carrying with it clues about the earliest epochs of galactic evolution. By studying this star in the context of the universe's 13.8 billion year timeline, we realize that we are latecomers to the cosmic party. Our sun is young. Our planet is young. Humanity is unimaginably young. And yet, there are stars like Kepler 444 that have been shining for most of cosmic history, long before us, and that will continue shining long after us. One of the most defining aspects of Kepler 444, beyond its incredible age, is its chemical composition. In astronomy, when scientists describe a star's makeup, they often use the term metallicity. But here's the important detail: astronomers use the word metal differently than we do in everyday life. In astrophysics, any element heavier than hydrogen or helium, such as carbon, oxygen, silicon, iron, magnesium, and beyond, is considered a metal. Hydrogen and helium are the primary building blocks of the universe, created in the Big Bang, while all heavier elements were forged later in the fiery deaths of stars. Kepler 444 is what astronomers call metal poor. Compared to our Sun, which has a relatively high metallicity, Kepler 444 contains far fewer heavy elements. This is not surprising, given its ancient age. The star was born more than 11 billion years ago, at a time when the Milky Way was still in its early stages of enrichment. The first generations of stars, massive, short-lived giants, had only just begun exploding as supernovae, scattering the first heavy elements into space. That means when Kepler 444 formed, the interstellar gas cloud from which it emerged contained mostly hydrogen and helium, with only trace amounts of the heavier elements needed to build rocky planets. By studying Kepler 444's spectrum, the detailed fingerprint of its light, astronomers can determine exactly what elements are present in its atmosphere. When light from the star is split into a spectrum, dark absorption lines appear at specific wavelengths, each corresponding to a particular element. In Kepler 444's case, the spectrum reveals extremely weak lines for metals like iron and magnesium, confirming its low metallicity nature. These measurements not only tell us what the star is made of, but also serve as a record of the cosmic environment at the time of its birth. The contrast with our Sun is stark. The Sun is often described as metal-rich, meaning it contains a relatively high proportion of heavy elements. About 2% of its mass is composed of elements heavier than hydrogen and helium. That may not sound like much, but it's crucial. Those metals allowed our solar system to form rocky planets like Earth, Venus, and Mars. Without them, the solar system might have been composed only of gas and ice. In fact, modern planet formation theories suggest that stars with higher metallicity are more likely to host planets, especially terrestrial ones. That's what makes Kepler 444 so surprising. Its metallicity is estimated to be around 1/3 that of the Sun, and yet it still managed to form 5 rocky planets. This discovery shook long-standing assumptions in astronomy. Previously, scientists believed that rocky planets couldn't form efficiently around stars with such low heavy element content. The logic was simple: fewer metals meant fewer solid building blocks, which should have prevented rocky planets from taking shape. And yet, Kepler 444 proves that even in a metal-poor environment, planetary systems can and do arise. This has far-reaching implications. If Kepler 444 could form rocky planets in such a barren environment, then planet formation must have been more widespread and more resilient than we ever imagined. That means that rocky planets might have been forming throughout the universe almost as soon as the first stars seeded space with even trace amounts of heavy elements. It suggests that worlds like Earth, or at least Earth-sized rocky worlds, could have been present in galaxies billions of years before our own solar system existed. Kepler 444's chemical composition also provides insights into the nature of its planets. Because the star is metal-poor, its planets are expected to be dense and rocky, rather than rich in volatile elements like water or methane. They likely contain a higher proportion of silicate rock and iron cores but lack the same diversity of elements available in Earth's composition. This makes them inhospitable by our standards, but it still demonstrates the astonishing fact that planetary architecture was already possible so early in cosmic history. The low metallicity of Kepler 444 also reinforces its status as a galactic fossil. Stars like it belong to the thick disk population of the Milky Way, a group of older, metal-poor stars that orbit the galaxy differently than younger, metal-rich stars like our Sun in the thin disk. By studying stars like Kepler 444, astronomers essentially look back into the formative period of the Milky Way, when the galaxy's chemistry was still raw and primitive. So, in essence, Kepler 444's chemical fingerprint tells a twofold story. On one hand, it is a relic of an era when the galaxy was young, poor in heavy elements, and still building itself. On the other, it challenges our assumptions by proving that planets can still form in such conditions. Its metal-poor nature is both a signature of its antiquity and a revelation that reshapes how we think about the universality of planet formation. When we talk about metallicity in stars, it might sound like a technical detail reserved for astrophysicists, but in reality, it has profound implications for the existence of planets, the possibility of life, and even our own origins. Metallicity is essentially the measure of how many heavy elements a star contains compared to hydrogen and helium. Since stars and planets form from the same primordial cloud of gas and dust, the chemical richness of that cloud determines what kind of system will emerge. That's why metallicity matters so much. It sets the stage for whether rocky worlds like Earth can form, or whether a star system will be left barren of terrestrial planets. In general, stars with higher metallicity are more likely to host planetary systems, especially ones with rocky planets. That's because heavy elements like silicon, magnesium, oxygen, and iron are the building blocks of solid planets. When a protoplanetary disk forms around a young star, it begins as a swirling pancake of gas and dust. The dust grains, composed of heavier elements, stick together, forming pebbles, then boulders, and eventually planetesimals. These planetesimals collide and merge, growing into full-fledged planets. Without enough heavy elements, this chain reaction struggles to get off the ground. This is why Kepler 444 is such a special case. By every expectation, a star as metal-poor as Kepler 444 shouldn't have been able to form multiple rocky planets. Its composition indicates that the protoplanetary disk from which it formed must have had only a fraction of the heavy element content of our solar system's disk. And yet, somehow, that limited material was enough to produce 5 Earth-sized planets. This discovery challenges the neat correlation scientists once assumed between metallicity and planet formation. It suggests that nature can be much more resourceful than our models predicted. But why is this so important for the broader story of the universe? Because metallicity doesn't just determine whether planets form, it determines when they can form. If planets required a high concentration of heavy elements, then planetary systems like ours could only arise much later in the history of the universe, after countless generations of stars had enriched the cosmos with metals. That would push the timeline for habitable planets billions of years forward. But Kepler 444 flips that idea on its head. It proves that planets could form very early, even when the universe was still young and relatively poor in metals. This revelation has direct implications for the search for life beyond Earth. Life, as we understand it, requires a rocky world with a solid surface, where chemistry can play out over billions of years. If such worlds could form as early as Kepler 444's system did, then the window for life to arise in the universe was opened far earlier than we once thought. Imagine worlds forming billions of years before Earth existed. If even a fraction of them had conditions suitable for life, then alien biospheres could have been evolving long before our planet's first microbes appeared. It also raises interesting questions about cosmic diversity. While Kepler 444's planets likely lack many of the volatiles and complex chemistry available to Earth, Their very survival for over 11 billion years proves that rocky planets can persist across cosmic time. This endurance demonstrates that planetary systems can remain stable and intact for nearly the entire history of the universe, providing incredibly long windows of opportunity for habitability, if not around Kepler-444 itself, then around other, similar systems. The importance of metallicity also extends to how astronomers search for planets today. Surveys have shown that stars with higher metallicity tend to host larger numbers of planets, especially gas giants like Jupiter. But Kepler-444 reminds us not to overlook the metal-poor stars, the ancient ones with sparse chemical richness. These stars might still host planets, even if the odds are lower, and studying them can reveal entirely new insights into the resilience of planetary formation. So why does all of this matter? Because it reframes the story of how common planets really are. The discovery of Kepler-444's planetary system tells us that the universe wasted no time in forming rocky worlds. Even in its earliest epochs, when stars like Kepler-444 were born from metal-poor gas, the recipe for planets was already in play. This means the cosmos is far richer in planets than we once dared to hope, and it means that the conditions for life might have existed long before our sun ever lit up the sky. Kepler-444 is not just remarkable for its age, it is remarkable for defying the rules we thought governed planet formation. Its existence proves that the connection between metallicity and planet building is not absolute. Even with limited heavy elements, nature found a way. And that resilience speaks volumes about the universe's ability to generate diversity, complexity, and perhaps even life. Kepler-444 is already fascinating as one of the oldest stars in the Milky Way, but what elevates it from a stellar curiosity to a cosmic marvel is that it hosts a planetary system, a family of worlds that have been orbiting their star for over 11 billion years. When astronomers announced this discovery in 2015, the scientific community was stunned. Here was not just an ancient star, but an ancient star with 5 confirmed exoplanets, all of them rocky, Earth-sized worlds. The Kepler mission was built to find such planets, but few expected to uncover an entire planetary system dating back almost to the dawn of the galaxy. The planets of Kepler-444 are officially designated Kepler-444b, C, D, E, and F, in order of increasing distance from the star. This naming follows the convention established by exoplanet discoveries. The host star keeps its name, and the planets receive lowercase letters starting with B. In the case of Kepler-444, the discovery of 5 planets was breathtaking not just in number, but in the fact that they all belong to the same compact system around such an ancient, metal-poor star. Each of these 5 planets is small and rocky, closer in size to Earth and Venus than to gas giants like Jupiter or Saturn. Their diameters range from about 0.4 to 0.75 times the size of Earth, placing them firmly in the category of terrestrial planets. Unlike many other exoplanetary systems discovered by Kepler, which often include large gas giants or super-Earths several times bigger than our planet, the Kepler-444 system is composed exclusively of small rocky worlds. This makes it unique in its composition, almost like a miniature version of the inner solar system, but compressed into a much tighter orbital arrangement. The planets were discovered using the transit method, Kepler's primary detection technique. The spacecraft measured tiny dips in the star's brightness whenever one of the planets crossed, or transited, in front of it. By carefully analyzing these dimmings of starlight, astronomers could not only confirm the presence of planets but also estimate their sizes and orbital periods. For Kepler-444, the detection of 5 distinct transit signals was clear evidence of a tightly packed planetary family. What makes the Kepler-444 planetary system particularly extraordinary is not just that it exists, but that it has survived intact for billions of years. The star has been through countless cycles of galactic evolution. It has orbited the Milky Way center dozens of times, passed through spiral arms, and endured gravitational interactions with other stars and cosmic structures. Through all of this, its 5 rocky planets have remained in stable orbits, circling faithfully around their parent star. This kind of stability over such immense timescales is almost unimaginable, and it underscores the resilience of planetary systems once they form. These planets, however, are not Earth-like in terms of habitability. Their proximity to Kepler-444 means they are too hot and too close to be in the habitable zone where liquid water could exist on their surfaces. But even if they cannot host life as we know it, they serve as crucial pieces of the cosmic puzzle. They prove that rocky planets were forming very early in the universe, and that such planets could endure across most of cosmic history. In many ways, the Kepler 444 system is like a time capsule. Each of its 5 planets represents a world older than Earth itself, older than our Sun, older than almost everything familiar in our corner of the galaxy. By studying them, astronomers are not only learning about one specific planetary system but also about the conditions of the early universe and the remarkable persistence of worlds over billions of years. In summary, Kepler 444 is not alone. It has a family of 5 Earth-sized planets, all tightly bound to their ancient star, all survivors of cosmic time. Their discovery stunned astronomers because it expanded the horizon of what we thought was possible. The fact that such a planetary system exists at all makes Kepler 444 one of the most compelling objects of study in the entire galaxy. When astronomers revealed the nature of Kepler 444's planets, one of the most astonishing details was their size. All 5 of the worlds in this system are small and rocky, remarkably similar to Earth and Venus. This was significant because most exoplanets discovered up to that point were either giant gas planets like Jupiter, or large rocky super-Earths much bigger than our own planet. But Kepler 444's planets belong to a rare group, true terrestrial worlds that fall within the same size range as those we're most familiar with here in our solar system. The planets of Kepler 444 range from about 0.4 to 0.75 times the diameter of Earth. To make that more concrete, the smallest among them is slightly larger than Mercury, while the largest is just a bit smaller than Venus. This puts them firmly into the category of rocky, terrestrial planets, worlds with solid surfaces rather than thick, gaseous envelopes. They are not the bloated mini-Neptunes or super-Earths that populate so many other exoplanetary systems. Instead, they are close cousins in size to our home planet. The fact that all 5 planets are so small is surprising given the system's age and chemical composition. Kepler 444 is metal-poor, meaning it formed with far fewer heavy elements than stars like our Sun. Since heavy elements are the essential raw materials for building rocky planets, astronomers once thought such stars would be unlikely to host multiple terrestrial worlds. And yet, Kepler 444 produced not just 1, but 5. Their very existence demonstrates that rocky planets are not an unusual outcome even in environments where the building blocks are scarce. This means the early universe may have been sprinkled with small, rocky worlds long before Earth appeared. Their sizes also matter because they hint at the likely composition of these planets. Worlds in the Earth to Venus size range are expected to be dominated by silicate rock and iron, with dense interiors and relatively thin atmospheres. Larger planets tend to accumulate thick gaseous envelopes, becoming more like mini-Neptunes, while smaller bodies often struggle to retain atmospheres at all. But planets in this size window sit at a balance point. They are large enough to hold onto atmospheres and sustain geological processes, but small enough to avoid becoming gas-shrouded giants. That balance makes them some of the most intriguing targets when astronomers search for potentially habitable conditions. Unfortunately, in Kepler 444's case, their orbits place them far too close to their parent star for habitability. Still, their size similarity to Earth and Venus makes them especially interesting to study because it suggests the physics of planet formation was already producing familiar planetary types when the universe was very young. Billions of years before our own solar system existed, processes were at work shaping rocky, Earth-sized worlds around stars like Kepler 444. Another fascinating aspect is the uniformity of their sizes. All 5 are within a relatively narrow range, with none of them being dramatically larger or smaller than the others. This suggests that the conditions in the star's protoplanetary disk were relatively stable, allowing similar-sized planets to form in close proximity. It also sets the Kepler 444 system apart from many others discovered by Kepler, where planets often vary widely in size within the same system. These planets, therefore, act as a bridge between our solar system and the earliest days of planet formation in the galaxy. They show us that even in a chemically young universe, the recipe for small, rocky planets was already working efficiently. And because their sizes mirror Earth and Venus, they remind us that our planet is not unique in size. It is part of a much larger pattern that seems to occur across the cosmos, even under very different conditions. So when we picture Kepler 444's planetary family, we should imagine 5 rocky, Earth, and Venus-sized worlds, circling tightly around their ancient orange dwarf star. They are not habitable, but they are profound in what they represent. some of the earliest terrestrial worlds in the galaxy, preserved in orbit for more than 11 billion years. The orbital arrangement of Kepler 444's planets is one of the most striking features of this ancient system. All 5 of its rocky worlds are huddled incredibly close to their star, far closer than Mercury is to our Sun. To put this into perspective, Mercury orbits the Sun at a distance of about 58 million kilometers, or 0.39 astronomical units, AU. In comparison, every single one of Kepler 444's planets completes its orbit at a distance significantly less than that, all of them confined to a region that would easily fit inside Mercury's path. It's as though the entire planetary system has been compressed into a tiny pocket of space around the star. Because they orbit so close, their orbital periods, the length of their year, are astonishingly short. While Earth takes 365 days to circle the Sun, and Mercury takes just 88 days, the planets of Kepler 444 complete their orbits in a matter of days. The innermost planet, Kepler 444b, races around the star in about 3.6 days, while the outermost of the 5, Kepler 444f, completes its orbit in roughly 10 days. This means that all 5 planets experience a full year in less than 2 weeks. Imagine living on a planet where you'd celebrate dozens of birthdays every Earth month. That's the bizarre reality of these worlds. The arrangement of these planets is what astronomers call an ultra-compact system. Their orbits are packed so tightly together that if they were transplanted into our solar system, all 5 would lie well inside Mercury's orbit, circling the Sun with dizzying speed. Yet despite this closeness, the system has remained stable for over 11 billion years. That fact alone is extraordinary. It suggests that planetary systems, once they find a balance, can endure immense stretches of cosmic time, surviving galactic interactions, nearby supernova explosions, and the chaotic environment of a galaxy still in its formative youth. This compactness also raises questions about how the system formed. One possibility is that the planets were born farther out in the star's protoplanetary disk and later migrated inward. Another is that they formed close to the star from the beginning, consuming what little rocky material was available in the ancient, metal-poor disk. Either way, their current arrangement tells us that planetary systems don't always look like ours. While we're used to the idea of planets spread across vast distances, Kepler 444 shows that nature sometimes builds planetary families in very tight configurations. Another fascinating detail is how the planets' orbits interact. Being so close together, they are likely in a state of orbital resonance, where their gravitational tugs on each other maintain stability. Resonance is a cosmic dance, locking planets into patterns that prevent them from colliding or destabilizing over time. These gravitational interactions may be part of why the Kepler 444 system has endured for billions of years without collapsing. It's also worth noting that being so near their star exposes these planets to intense radiation and heat. Any atmospheres they might have once possessed could have been stripped away long ago. Their rocky surfaces are probably scorched, perhaps covered in molten rock seas or barren crusts baked under relentless stellar light. From our perspective, they are uninhabitable. But from a scientific perspective, they are invaluable, because their arrangement reveals the diversity of planetary systems and proves that compact configurations can survive across cosmic ages. If you compare this arrangement with our own solar system, the contrast is staggering. In our neighborhood, the planets are spread out, with increasing distances as you move outward. Mercury, Venus, Earth, and Mars occupy orbits spaced tens of millions of kilometers apart. Beyond them lie the gas giants and icy worlds, expanding the solar system to incredible scales. Kepler 444, by contrast, is like a miniature model of only the inner solar system, shrunk down to a fraction of the size and orbiting at blistering speeds. This compact system is a reminder that the universe doesn't follow a single blueprint for planetary systems. Our solar system is just one variation among countless possibilities. The Kepler 444 system shows us that stars can host multiple Earth-sized planets all squeezed into a space smaller than Mercury's orbit, and that such arrangements can last not just for millions, but for billions of years, nearly the entire history of the galaxy. In the end, the orbital arrangement of Kepler 444's planets makes them both alien and familiar. They are Earth-sized worlds, like ours, but racing around their star in orbits so tight that an entire planetary system would fit into the inner edge of our own. It's a cosmic reminder of the creativity of nature, building worlds in configurations we might never have imagined, and preserving them for nearly 11 billion years. When astronomers look at exoplanetary systems, one of the first questions that arises is, are any of the planets in the habitable zone? The habitable zone, sometimes nicknamed the Goldilocks zone, is the region around a star where temperatures are just right for liquid water to exist on a planet's surface. It's not too hot and not too cold, making it the most promising area for the development of life as we know it. For our Sun, the habitable zone stretches roughly from just beyond Venus's orbit out to somewhere between Earth and Mars. Earth sits comfortably within it, which is one reason why our planet has oceans, rivers, and the conditions necessary for life. Unfortunately, in the case of Kepler 444, none of its 5 known planets fall within this habitable zone. Instead, all of them orbit far too close to their star. Their distances are so small that they would all fit easily inside the orbit of Mercury, which is already far too hot to host liquid water. The closest planet in the system, Kepler 444b, completes its orbit in just 3.6 days, meaning it is literally hugging its star. The outermost planet, Kepler 444f, orbits in just about 10 days, still well within a region of extreme heat and radiation. Because the star is a K-type orange dwarf, cooler and dimmer than our Sun, the habitable zone is closer in than it would be for a solar-type star. However, even accounting for the star's lower luminosity, the habitable zone of Kepler 444 still lies much farther out than the orbits of its planets. That means all 5 are baked by their star's radiation, receiving many times the amount of energy Earth gets from the Sun's surface. Temperatures on these planets almost certainly high enough to sterilize them completely, preventing liquid water from ever existing. If they once had atmospheres, they were likely stripped away long ago by the relentless stellar wind and radiation. In practical terms, this makes them uninhabitable worlds. They are rocky, Earth-sized planets, but they are not Earth-like. Instead of oceans and continents, they might be covered in scorched rock or molten lava seas. Any attempt to stand on their surfaces, if such a thing were possible, would mean enduring blistering heat under a harsh orange sky. This reality highlights one of the great truths about exoplanet science. Just because a planet is Earth-sized does not mean it is Earth-like. Size alone is not enough. Distance from the star, atmospheric retention, chemical composition, and magnetic shielding all play a role in determining habitability. Kepler 444 reminds us of this by presenting a planetary family that looks familiar in size but fails completely in conditions for life. And yet, their uninhabitable nature does not diminish their importance. In fact, it makes them even more scientifically intriguing. The existence of rocky planets so close to an ancient, metal-poor star proves that the universe was producing terrestrial worlds almost from the beginning, even if those worlds were not places where life could thrive. They show us that the blueprint for making Earth-sized planets was active very early in the galaxy's history, long before Earth itself was even a possibility. What's more, the inhospitable conditions of Kepler 444's planets spark a deeper reflection. If rocky planets like these could form so early, then surely some of them elsewhere in the universe must have ended up in the habitable zones of their stars. That means the potential for life-supporting planets stretches back much farther in cosmic history than we once believed. While Kepler 444's planets may be barren, they act as proof of concept for the early universe's ability to generate Earth-sized worlds. It's also worth considering that habitability is not a static concept. What we consider too hot today might have looked different billions of years ago under different atmospheric conditions. But given the intense radiation and proximity of these planets to their star, it is safe to say they have never enjoyed Earth-like conditions. Their fate is to remain scorched and sterile, not blue and life-filled. In the end, the absence of habitable planets in Kepler 444's system does not make it less extraordinary. It makes it even more compelling, because it reminds us that not every rocky planet is destined to be a cradle of life. Some are destined to be barren survivors, orbiting faithfully for billions of years, teaching us lessons about the history of the galaxy and the resilience of planetary systems. The Kepler 444 system is one of the most extraordinary examples of a compact planetary system in the galaxy. When astronomers say compact, they don't just mean that the planets are close together, they mean that the entire planetary family is squeezed into a region so tight, so condensed, that by comparison our solar system looks vast and sprawling. All 5 of Kepler 444's rocky worlds complete their orbits in just a handful of days, ranging from about 3.6 days for the innermost planet to just under 10 days for the outermost. That means the entire system, all 5 planets, is tucked inside a space smaller than the orbit of Mercury, our solar system's innermost planet. To understand how compact this is, let's compare it with Earth. Our planet takes 365 days to orbit the Sun. Mercury, the speedster of our solar system, still requires 88 days for a full orbit. Yet Kepler 444's planets circle their star so quickly that they would live through dozens, even hundreds, of years in the time it takes Earth to complete one. Imagine living on Kepler 444b. Your birthday would come every 3.5 Earth days. On Kepler 444f, the longest year in the system, your birthday would still arrive every 9.7 Earth days. Their calendars, if they had them, would be frantic, racing by in a blur compared to the leisurely pace of our world. What makes this so fascinating is the stability of the arrangement. Compact systems are inherently delicate. Planets this close together exert strong gravitational tugs on each other. If they were not arranged in a finely balanced pattern, their orbits could destabilize over time, leading to collisions or ejections. And yet, Kepler 444's system has endured for more than 11 billion years without falling apart. This means the planets are locked in a stable gravitational configuration, possibly maintained through orbital resonances, a cosmic choreography where each planet's orbit is synchronized with the others in a repeating rhythm. Resonance acts like a stabilizing metronome, preventing the planets from drifting into dangerous encounters. From a formation standpoint, such compactness is puzzling. Did these planets form close to their star from the very beginning, or did they migrate inward after forming farther out in the protoplanetary disk? Migration is a well-established process in planetary science, where interactions with the disk cause planets to spiral inward. If this happened here, it would mean the system once looked very different, but eventually compressed into its current state. Alternatively, the planets may have formed exactly where they are, consuming the limited material in the star's ancient, metal-poor environment to build themselves. Either scenario stretches our understanding of planetary formation. Compact systems like Kepler 444 are not entirely unique. Astronomers have discovered other ultra-compact systems such as TRAPPIST-1, where 7 Earth-sized planets orbit within a similarly tight space. But what makes Kepler 444 stand apart is its age. TRAPPIST-1 is relatively young compared to the 11-billion-year-old Kepler 444. That means this compact arrangement isn't just a temporary quirk of planetary formation. It can persist across almost the entire lifetime of the galaxy. This realization changed how scientists view the long-term survival of compact systems. Another remarkable consequence of such tight orbits is the intensity of the environments these planets experience. Being so close to their star, they are blasted with radiation and tidal forces. The innermost worlds may even be tidally locked, always showing the same face to their star, much like the Moon always shows one face to Earth. This would create dramatic worlds with a blazing hot day side and a freezing cold night side. And yet, despite these extreme conditions, the system as a whole has remained dynamically peaceful, orbiting in harmony for billions of years. From our perspective, the compactness of Kepler 444's planets is a humbling reminder that planetary systems come in astonishingly diverse architectures. Our solar system spreads its planets over billions of kilometers, with gas giants lurking far from the Sun and small rocky worlds closer in. Kepler 444, by contrast, is a system entirely focused inward, packing 5 Earth-sized planets into a region where we would expect perhaps only 1 or 2. Both systems are valid outcomes of the planet-forming process, showing us that the universe doesn't adhere to a single template. In a way, Kepler 444 is like a miniature planetary clock. Each planet ticks around its star at lightning speed, locked into a rhythm that has been stable for almost the entire age of the Milky Way. This cosmic timepiece has been keeping perfect time since before Earth existed, and it will likely continue ticking long after our planet is gone. So, the compact system of Kepler 444 is more than just a curiosity. It's a testament to the resilience of planetary systems, the creativity of nature in arranging worlds, and the fact that there are many different paths to building a family of planets. Where we see impossibility, 5 planets squeezed into an orbit tighter than Mercury's, the universe sees stability, endurance, and beauty. When we think about a planetary system lasting for billions upon billions of years, it almost seems unimaginable. Planetary systems are fragile by nature. Planets exert gravitational pulls on each other, stars evolve, galaxies tug and twist systems as they orbit through space. Over such enormous spans of time, you might expect chaos to inevitably break loose. Yet the Kepler 444 system has astonished astronomers because it has remained remarkably stable for more than 11 billion years. This stability is one of its most defining and scientifically important features. To appreciate the magnitude of this endurance, let's remember what the universe was like when Kepler 444 formed. The Milky Way was still young and chaotic, teeming with massive stars exploding as supernovae, and galaxies were colliding more frequently than today. Our Sun, the Earth, and the entire solar system wouldn't exist for another 6.5 billion years. Despite being born into such a violent cosmic neighborhood, Kepler 444 and its 5 tightly packed planets found a delicate balance early on, and they have maintained it ever since. So how does such a fragile-looking planetary system avoid tearing itself apart? The answer lies in the precision of its gravitational architecture. The planets orbit very close to their star, but they do so in a synchronized way, likely through orbital resonances or near resonances. Resonances are gravitational patterns where the orbital periods of planets are related by simple ratios. For instance, one planet might orbit exactly twice for every 3 orbits of its neighbor. These patterns prevent the planets from pulling each other into unstable paths. Instead of colliding or drifting into chaotic interactions, they remain locked in a kind of cosmic choreography. Think of it like dancers on a stage, moving in a carefully timed routine. If even one dancer is out of step, the whole performance can collapse into chaos. But when every movement is synchronized, the dance can continue flawlessly, night after night. Kepler 444's planets have been performing their gravitational dance flawlessly for nearly the entire history of the galaxy. That is extraordinary. Another reason for this system's stability comes from the star itself. Kepler 444 is a K-type orange dwarf star. Smaller and less energetic than our Sun stars like this burn their fuel more slowly, evolving at a gentler pace. That means fewer dramatic changes in luminosity or radiation output over time, allowing the planets to orbit in relative calm. If the star had been a massive, short-lived star, it might have exploded in a supernova billions of years ago, destroying its planets in the process. Instead, Kepler 444's modest size and stable output created an environment where planets could endure for eons. On top of that, K-type stars are known for their longevity. While our Sun's total lifespan is estimated at about 10 billion years, K-type stars can last 20 to 30 billion years or more. This means that Kepler 444 is still only in its middle age, despite already being older than the Earth by 6.5 billion years. Its planets may remain in orbit for billions more years to come. The stability we see today is not just a relic of the past, it's a promise for the future. What's even more incredible is that this system has survived galactic dynamics. Over billions of years, as the Milky Way rotates, stars pass close to one another. Gravitational nudges from passing stars, massive clouds of gas, or even tidal forces from the galaxy's spiral arms could have destabilized the system. Yet Kepler 444 seems to have endured all of these galactic events without losing its planetary harmony. This makes it not just stable, but also resilient on a cosmic scale. The long-term stability of Kepler 444 raises important questions for science. How many other systems like this exist, quietly orbiting in harmony for billions of years? Could there be planetary systems that have hosted stable, habitable worlds for far longer than Earth has existed? If so, what might that mean for the possibilities of ancient extraterrestrial life? Kepler 444's endurance reminds us that the conditions for stability are not rare, they may be common, and that means the opportunities for life could also be far more widespread than we once thought. From a symbolic perspective, Kepler 444's stability feels almost poetic. Here is a planetary system that has survived almost everything the universe could throw at it. It has witnessed the birth of countless generations of stars, the merging of galaxies, the rise and fall of entire civilizations on Earth, and through it all, its planets continue to circle faithfully, never faltering. If cosmic time could be measured in heartbeats, Kepler 444's system is the steady, unwavering pulse of the galaxy itself. Ultimately, the stability of Kepler 444 is not just a scientific curiosity, it's a revelation. It tells us that planetary systems can be built to last, even under the harshest conditions, and that the story of planets in the universe is much older and more enduring than the story of our own solar system. It challenges us to think about the resilience of the cosmos, and how life, if it emerged elsewhere, might have had far more time to develop than we've ever had here on Earth. One of the most astonishing revelations from the study of Kepler 444 is the sheer longevity of its planets. When scientists first discovered exoplanets in the late 20th and early 21st centuries, many assumed that planets, especially those orbiting very close to their stars, were fragile and transient. The prevailing models suggested that over billions of years, interactions between planets, gravitational perturbations, and stellar evolution could destabilize planetary systems. Gas giants might migrate, small rocky planets could be ejected from their orbits, and the intense radiation from stars could strip atmospheres and even destroy planets in close orbits. By these assumptions, a planetary system as old and compact as Kepler 444's should have been long gone, or at least drastically altered. Yet Kepler 444 defies all these expectations. Its 5 small, rocky planets have survived intact for over 11 billion years, a timescale that is almost incomprehensible. To put that in perspective, Earth has existed for only about 4.5 billion years, less than half the age of these planets. The Sun has undergone less than half of its expected lifespan, while Kepler 444's planets have already endured more than twice that. This survival demonstrates that planetary systems can be far more durable than early theoretical models predicted. What makes this even more remarkable is the planet's proximity to their star. All 5 orbit extremely close to Kepler 444, much closer than Mercury's orbit around the Sun. Close-in planets experience intense gravitational forces, tidal interactions, and stellar radiation, all of which have the potential to destabilize or erode them over time. Despite this, these planets have remained in stable orbits, suggesting that once a planetary system achieves a balanced configuration, it can maintain that balance for billions of years. Their longevity challenges our assumptions about how fragile planets really are. The survival of these planets also provides critical insight into planet formation in the early universe. Kepler 444 formed when the universe was still young and relatively metal-poor, meaning there were fewer heavy elements available for building planets. Earlier models assumed that low metallicity stars would struggle to form planets at all, and that any planets that did form would be small, few in number, or unstable. Kepler 444's system proves that this is not necessarily the case. Even in chemically sparse environments, rocky planets can form and endure for almost the entire history of the galaxy. This endurance has profound implications for the potential for life elsewhere in the universe. If planets can survive for over 11 billion years, it raises the possibility that some of them may have had long enough stable periods to allow life to develop, evolve, and perhaps even reach advanced stages, long before Earth even existed. Even though Kepler 444's planets are too close to their star to be habitable, their existence proves that other long-lived, stable planets could have existed in more favorable orbits, giving life a head start of billions of years. The stability and survival of Kepler 444's planets also force us to reconsider the timescales of planetary evolution and galactic history. Most of the planets discovered to date are relatively young, orbiting stars that are only a few billion years old. Observing a system like Kepler 444 allows scientists to see the result of nearly the entire age of the galaxy compressed into a single system. It demonstrates that planets are not fleeting accidents. They can be cosmic survivors, enduring despite galactic events, stellar evolution, and the passage of unimaginable amounts of time. Another remarkable aspect of planetary survival in Kepler 444 is the uniformity and compactness of the system. Systems with planets closely packed together are often thought to be inherently unstable because small gravitational perturbations can grow over time. Yet these planets remain in perfect harmony. This longevity suggests that planetary systems, once formed with the right configuration, are self-stabilizing, capable of persisting across cosmic timescales without significant disruption. From a philosophical perspective, the survival of these planets is humbling. The Earth, our solar system, and human civilization exist for just a fraction of cosmic history. Meanwhile, Kepler 444's planets have orbited their star for billions of years longer than the age of the Earth, silently witnessing the growth of galaxies, the formation and destruction of stars, and the rise of life elsewhere, if it ever arose. These planets are essentially living fossils, preserving a record of the earliest epochs of planetary formation. In short, Kepler 444 has rewritten our understanding of planetary longevity. It proves that planets can be enduring, robust, and stable over nearly the entire history of the universe. They challenge early assumptions that planets are fragile or short-lived, showing instead that once a planetary system achieves stability, it can survive cosmic upheavals and extreme conditions. The planets of Kepler 444 are not only survivors, they are testaments to the resilience of worlds, enduring silently for more than 11 billion years. The discovery of Kepler 444 and its 5 rocky planets has profound implications for habitability, even though none of its worlds fall within the star's habitable zone. At first glance, the fact that these planets orbit so close to their star, experiencing scorching temperatures and relentless radiation, might seem like a dead end for discussions of life. Yet when we step back and consider the bigger picture, Kepler 444 opens a window into the early universe and the possibility that rocky, potentially life-supporting worlds may have existed far earlier than previously thought. Kepler 444 formed over 11 billion years ago, at a time when the universe was only about 2.6 billion years old. This means that its planets were among the first generation of rocky planets in the Milky Way. The very fact that they exist demonstrates that the mechanisms of planet formation were already working efficiently in metal-poor environments. Scientists once believed that low metallicity would severely limit the creation of rocky worlds because metals provide the essential building blocks: silicon, iron, magnesium, oxygen, and carbon for solid planets. Kepler 444 shattered that assumption, proving that rocky planets could form even when heavy elements were scarce. If rocky planets could form in the metal-poor conditions surrounding Kepler 444, it follows that other stars forming in similar environments could have also produced terrestrial worlds. Some of these planets may have ended up in habitable zones around their parent stars, where conditions for liquid water and, potentially, life were favorable. This extends the timeline for the potential development of life far back into cosmic history, billions of years before the Earth itself existed. The universe may have had habitable planets nearly from its youth, providing enormous windows of opportunity for life to emerge. Kepler 444 also illustrates that planetary formation is resilient. Even with a compact system, tight orbital spacing, and extreme proximity to its star, the planet survived billions of years. If this system could persist for such an immense timescale, it is reasonable to assume that rocky planets formed farther out in more temperate zones could survive as well, providing stable environments for extended periods. Stability is a key requirement for habitability. Planets need millions or billions of years for life to evolve from simple molecules into more complex organisms. Kepler 444 shows that planets can persist long enough for that potential to exist. Moreover, the existence of these planets challenges prior assumptions about the earliest epochs of planet formation. Before the discovery of Kepler 444, many scientists assumed that rocky planets required generations of stars to enrich the interstellar medium with metals. That would have meant that habitable planets could not exist until the galaxy had matured, several billion years after the Big Bang. Kepler 444 demonstrates that rocky planets, while small and close in, were forming even when the universe was young and relatively primitive. This raises the tantalizing possibility that some earlier formed planets elsewhere could have possessed the right conditions for life, long before our solar system appeared. In practical terms, this reshapes the way we think about the search for extraterrestrial life. While exoplanet surveys often focus on stars similar to the Sun and planets in the habitable zone, Kepler 444 teaches us that ancient systems, even metal-poor ones, can yield important insights. Rocky planets might have been widespread in the early universe, meaning the potential for habitable environments, and perhaps life itself, may extend far further back in time than previously imagined. We are only scratching the surface of a galaxy that has been forming planets for more than 11 billion years. Additionally, the implications are philosophical as well as scientific. The fact that rocky planets existed so early raises questions about whether life elsewhere could have a head start of billions of years on Earth. If life ever emerged on an early, habitable planet orbiting a metal-poor star, it could have evolved, diversified, and perhaps even advanced technologically long before our planet formed. Kepler 444 serves as a reminder that the universe's timeline is vast and that Earth and humanity are newcomers to a cosmos that has been experimenting with planets and potentially life for eons. Finally, the existence of Kepler 444's planets inspires a reconsideration of planetary abundance in the galaxy. If rocky planets could form around a metal-poor star over 11 billion years ago, then terrestrial worlds may be far more common than previously thought, scattered throughout the Milky Way in systems both ancient and young. Even though the planets of Kepler 444 themselves are inhospitable, their presence proves that the universe was already capable of creating rocky worlds at a time when the galaxy was still in its formative stages. That's a key takeaway for understanding habitability. The ingredients for life, and the platforms for it, rocky planets, may have existed for most of cosmic history, long before Earth appeared. In essence, Kepler 444 reframes our understanding of early planetary habitability. It is a system that may not host life itself, but it proves that rocky worlds were already emerging early in the universe, surviving for billions of years, and providing the potential canvas for life in other corners of the cosmos. This discovery expands our perspective, reminding us that habitable conditions, while rare, may have been possible far earlier and far more widely than we ever imagined. The discovery of Kepler 444 and its 5 ancient rocky planets opens up one of the most profound questions in astrobiology. If terrestrial planets were forming more than 11 billion years ago, could life have begun elsewhere long before Earth even existed? This possibility challenges our conventional timeline of life and forces us to consider a universe where habitable conditions, and perhaps life itself, preceded our solar system by billions of years. Kepler 444 formed just 2.6 billion years after the Big Bang, and its planets formed shortly afterward. While these specific planets are too close to their star to support life due to extreme heat, their existence proves that rocky planets could arise even in metal-poor environments. This implies that other planets forming in similar conditions, but situated at more favorable distances from their stars, could have maintained temperate surfaces where liquid water and complex chemistry might occur. In other words, the universe had the capacity to generate life-supporting worlds long before our Sun ignited. The timescales involved are staggering. Earth formed about 4.5 billion years ago, and life appeared relatively quickly, within a few hundred million years. But Kepler 444's planets, and potentially similar ancient planets elsewhere, have been around for more than 11 billion years. If habitable conditions existed on planets orbiting other ancient stars, life could have had billions of years to evolve. For comparison, all of Earth's biological history, from simple microbes to intelligent beings, spans only a fraction of that time. Life elsewhere could, theoretically, be far older, far more complex, and perhaps even technologically advanced relative to humanity. This possibility also reframes our understanding of the conditions necessary for life. Traditionally, scientists focused on stars like the Sun, assuming that metallicity and relative youth were critical for forming habitable planets. Kepler 444 challenges that assumption. Life might not require a perfectly sun-like star or a high metallicity environment. Rocky planets forming around ancient stars could have offered stable surfaces, ample time, and chemical diversity sufficient for prebiotic chemistry and the emergence of life. One intriguing implication of this idea is that the universe could host ancient biospheres, ecosystems that have existed far longer than life on Earth. If life arose on planets orbiting ancient stars like Kepler 444 or similar systems, those organisms could have evolved strategies, biochemistry, and complexities that Earth life has not yet reached. Perhaps microbial life on these worlds progressed into multicellular life billions of years before Earth's first complex organisms appeared. Another consideration is planetary stability. Kepler 444 shows that planets can survive in compact configurations for over 11 billion years. This stability is essential for life because it allows a planet to maintain consistent conditions over geological and biological timescales. If a planet's orbit were highly chaotic, temperatures and radiation exposure could fluctuate too wildly to support sustained life. The long-lived and stable planets orbiting stars like Kepler 444 suggest that the cosmic conditions for life have existed for the majority of the universe's history. This also leads to fascinating possibilities for the distribution of life across the galaxy. If ancient rocky planets existed around stars similar to Kepler 444, they might have seeded the galaxy with life long before the solar system formed. In principle, interstellar panspermia, where life or its building blocks travel between star systems, could have spread prebiotic molecules or even simple life forms across the galaxy. While this remains speculative, the concept underscores that life could have had a head start of billions of years compared to Earth. Of course, the precise timing of life's origin is unknown. Even if rocky planets formed early, life might require certain conditions: stable atmospheres, magnetic fields, and chemical abundance that may have been rare in the early universe. Yet the existence of Kepler 444's planets demonstrates that the necessary foundation, terrestrial worlds, was in place extremely early. This alone dramatically expands the window of opportunity for life's emergence. Philosophically, this perspective is humbling. Humanity often imagines itself as among the earliest intelligent life forms in the cosmos. Yet if ancient stars hosted habitable worlds billions of years before Earth formed, life elsewhere could be unimaginably older. Civilizations, if they arose, might have had enough time to develop technologies, explore their systems, or even influence the galaxy in ways we cannot yet imagine. Our existence is just a recent episode in a universe teeming with deep history. In essence, Kepler 444 allows us to entertain a cosmic narrative in which the universe has been experimenting with life for nearly its entire existence. Rocky planets formed early, some potentially habitable, stable for billions of years, offering immense timescales for biology to develop. While we have yet to discover life beyond Earth, the very possibility of ancient life elsewhere is now more plausible than ever, reshaping our understanding of how life could have unfolded long before our planet even appeared. When we place Kepler 444 within the timeline of cosmic history, the contrast with Earth is staggering. Kepler 444 formed over 11 billion years ago, which means it existed more than twice as long as our own Sun and its planets have. To put this in perspective, the Earth would not even appear for another 6.5 billion years after Kepler 444 was already in place, orbiting steadily with its 5 rocky planets. While we often think of the Earth as ancient and enduring, it is in fact a relatively young planet, a newcomer in a galaxy that has been forming stars and planets for billions of years prior to our solar system's birth. This immense difference in age emphasizes just how early Kepler 444 and its planets were part of the Milky Way. When Kepler 444 was forming, the universe was still in its adolescence. Galaxies were merging, stars were igniting at a furious pace, and the chemical elements necessary for life and planet formation were only beginning to accumulate through generations of stellar evolution. Meanwhile, the material that would eventually coalesce into our Sun and planets, including Earth, was still dispersed across interstellar clouds, waiting billions of years for the right conditions to condense into a star system. The age comparison also highlights the vast temporal scale of the universe. Kepler 444 is like a living fossil, a relic of a bygone era when the galaxy was chemically primitive and planet formation was just getting started. By contrast, Earth is a product of a later epoch, born when the universe had already matured, heavy elements were abundant, and the Milky Way had settled into a relatively stable configuration. The Earth, as familiar as it feels to us, is only a recent development in the cosmic story. This temporal gap, 6.5 billion years, is almost unfathomable when considering human history. For reference, Homo sapiens have existed for roughly 300,000 years, a mere blink of an eye compared to the age of Kepler 444 or the span separating its formation from Earth's. In that sense, Kepler 444 has been orbiting its star, sustaining its compact system of rocky planets, and witnessing cosmic events for billions of years before Earth even existed. From a cosmic perspective, Earth is not a pioneer but a latecomer, arriving long after some planetary systems had already stabilized and persisted for eons. The age difference also underscores the potential for ancient life elsewhere in the galaxy. If rocky planets like those around Kepler 444 could survive for billions of years, then planets that formed earlier than Earth had the opportunity to maintain stable, life-supporting conditions long before our planet appeared. By the time Earth was forming in the relatively mature solar nebula around the Sun, other planets in systems like Kepler 444 could have already completed billions of years of evolution. In other words, life elsewhere could be billions of years older than life on Earth if it ever arose. Furthermore, the comparison invites reflection on the timescales of planetary and stellar evolution. Kepler 444 is a K-type orange dwarf star, smaller and cooler than our Sun, with a lifespan that will far exceed the Sun's total life expectancy. This means that while Earth and the solar system have only been around for 4.5 billion years, Kepler 444's planets have endured for more than twice that amount, and the star will continue shining stably for billions more. In essence, Earth's history is just a chapter in a much longer narrative, while Kepler 444's system represents a saga spanning nearly the entirety of the Milky Way's history. This comparison also shifts our perspective on the concept of cosmic age and what it means to be old or young. While Earth may feel ancient to us, it is relatively youthful in the galactic sense. Kepler 444, in contrast, is an elder statesman of the Milky Way, a witness to the early epochs of star formation and the initial emergence of rocky worlds. Its planets are time capsules that preserve conditions from a universe that looked very different from today, offering a direct connection to the galaxy's formative years. Ultimately, the fact that Earth wouldn't exist for another 6.5 billion years after Kepler 444 formed forces us to reconsider our place in cosmic history. Our solar system is a late addition, a participant in a long-running story that began with stars and planets like Kepler 444 billions of years earlier. The comparison reinforces the notion that the universe is vast not only in space but in time, and that many planetary systems, formed long before Earth, may have had opportunities for evolution, stability, and perhaps life far earlier than our own. Studying Kepler 444 is not just about understanding a single star or its planets, it's about peering back into the history of the Milky Way itself, a process astronomers call galactic archaeology. This term may sound poetic, but it captures the essence of what scientists are doing, using ancient stars and their planetary systems as tools to reconstruct the timeline, composition, and evolution of our galaxy. Just as archaeologists dig through layers of soil to uncover human history, astronomers examine stars like Kepler 444 to uncover the formative events of the Milky Way, billions of years before our solar system ever existed. Kepler 444 is over 11 billion years old, making it nearly as old as the Milky Way itself, which is estimated to be around 13.6 to 13.8 billion years old. Because it formed so early, its chemical composition, structure, and planetary system serve as a fossil record of the early galaxy. Unlike younger stars, which have inherited a rich mix of heavy elements from generations of supernovae, Kepler 444 is metal-poor, containing far fewer elements heavier than helium. This tells astronomers that it formed during a period when the galaxy was still chemically primitive, providing direct evidence of the conditions that existed during the galaxy's youth. By analyzing the properties of stars like Kepler 444, astronomers can reconstruct the sequence of star formation and the buildup of elements in the Milky Way. Each ancient star carries clues about the rate of stellar births, deaths, and chemical enrichment in its era. For example, the low metallicity of Kepler 444 indicates that only a few generations of massive stars had exploded as supernovae before it formed. Its very existence demonstrates that planetary formation was already underway despite the scarcity of heavy elements, offering insight into the early processes that built rocky worlds across the galaxy. Planetary systems, like Kepler 444's 5 rocky planets, add another layer to this galactic archaeological record. Their survival for more than 11 billion years shows that stable planetary systems could emerge even under early galactic conditions. Studying their orbital architecture, size, and composition provides information not only about planet formation but also about the dynamics of the early Milky Way, including gravitational interactions with other stars, gas clouds, and the structure of the galactic disk. These planets act as cosmic time capsules, preserving the conditions of the young galaxy far better than stars alone can. Galactic archaeology relies on several tools and techniques to extract this information. For Kepler 444, astronomers have used spectroscopy to measure the star's chemical composition, revealing its metal-poor nature. They have used astroseismology, the study of stellar vibrations, to determine its precise age. By combining these methods with observations of the star's planets and their orbits, scientists can paint a detailed picture of what the Milky Way looked like more than 11 billion years ago. Each piece of data is like a fragment of an ancient manuscript, giving us insight into epochs that would otherwise be lost to time. This approach also allows astronomers to trace the assembly of the galaxy over cosmic time. Ancient stars like Kepler 444 may have formed in small proto-galactic fragments, long before the Milky Way took on its current spiral shape. By studying the kinematics and chemistry of these stars, scientists can infer how the galaxy grew through mergers and accretion, revealing the long and tumultuous history of our cosmic neighborhood. In this way, Kepler 444 is not just an old star, it is a key witness to the galaxy's formative events, a living record of processes that occurred billions of years before the Earth existed. Galactic archaeology also has implications for understanding the earliest potential for life in the universe. By identifying ancient stars with rocky planets, scientists can estimate when habitable conditions could have first arisen. While Kepler 444's planets themselves are too close to the star to host life, their very existence shows that rocky planets were forming early, meaning habitable planets could have emerged elsewhere in the galaxy billions of years before Earth. Studying such stars gives us a broader context for the timeline of life, offering a cosmic perspective on how early the universe became capable of supporting biology. In many ways, studying Kepler 444 is like holding a key to the galaxy's past. Each measurement, each detail of its age, composition, and planetary system, is a piece of evidence that helps reconstruct the Milky Way's early chapters. This approach transforms our view of stars from isolated objects into archival records of cosmic history. They are the fossils and artifacts of a galactic civilization we cannot see directly, but whose traces are embedded in the light and planets we observe today. Finally, Kepler 444 illustrates why ancient stars are invaluable to modern astronomy. Younger stars can tell us about present conditions and the more recent history of the galaxy, but only ancient stars like Kepler 444 can show us the galaxy's infancy. Their planets, remarkably, can survive for billions of years, preserving the conditions of early planetary formation. In this sense, Kepler 444 is not just a star, it is a time machine, a portal that allows astronomers to study an epoch of the Milky Way that predates the solar system by billions of years. Through galactic archaeology, we gain a profound sense of perspective. The Milky Way is not just a backdrop for our solar system. It is a dynamic, evolving entity with billions of stars and countless planets, each with its own history. Kepler 444 connects us to the earliest chapters of that story, reminding us that our Sun and Earth are just the latest additions to a galaxy that has been forming worlds for nearly the entire age of the universe. Understanding Kepler 444 and its ancient planetary system has been made possible through the advanced astronomical techniques of spectroscopy and astroseismology, among others. These methods allow scientists to probe stars and planets in ways that are otherwise impossible, providing insight into their composition, age, structure, and dynamics. Each technique acts like a different tool in a cosmic laboratory, helping us unravel the story of one of the oldest known stars in the Milky Way. Spectroscopy is one of the most fundamental tools in modern astronomy. By analyzing the light emitted by a star, scientists can determine its chemical composition, temperature, and motion. Every element absorbs and emits light at specific wavelengths, creating a distinct spectral fingerprint. By studying these fingerprints in Kepler 444's light, astronomers discovered that it is metal-poor, containing fewer elements heavier than hydrogen and helium compared to younger stars like our Sun. This low metallicity indicated that Kepler 444 formed during the early stages of the galaxy, when fewer generations of stars had synthesized heavy elements. Spectroscopy also allows astronomers to measure radial velocity, tiny wobbles in a star's motion caused by orbiting planets, which can provide additional evidence of a planetary system, although in Kepler 444's case, the planets were primarily discovered through transits rather than direct spectroscopic measurement. Another indispensable technique is astroseismology, which is essentially the study of stellar quakes. Stars are not rigid, they pulsate and vibrate due to internal pressure waves moving through their interiors. These oscillations slightly modulate the star's brightness over time. By observing these subtle fluctuations in Kepler 444's light, scientists could determine its internal structure with extraordinary precision. Astroseismology allows astronomers to measure the star's density, radius, and, most critically, its age. For Kepler 444, these vibrations revealed an age of over 11 billion years, making it one of the oldest known stars in the Milky Way. Without this technique, such a precise age estimate would be nearly impossible, especially for a star so distant and faint. In addition to spectroscopy and astroseismology, the transit method played a key role in studying the planetary system. The Kepler Space Telescope, which discovered the planets in 2015, monitored the star's brightness over extended periods. When a planet passes in front of the star from our viewpoint, it causes a tiny dip in brightness, known as a transit. By analyzing the frequency, depth, and duration of these dips, astronomers determined that Kepler 444 hosts 5 small, rocky planets. The transit data allowed scientists to measure the planets' sizes and orbital periods, revealing the extremely compact configuration of the system. Combining these techniques provides a remarkably detailed picture. Spectroscopy tells us what the star is made of and how it moves, astroseismology reveals its internal structure and age, and the transit method uncovers the existence and dimensions of its planets. Together, these methods enabled astronomers to construct a comprehensive model of Kepler 444, including its unusual age, metal-poor composition, and its family of tightly packed Earth-sized planets. Other methods also contribute indirectly. For instance, stellar modeling and theoretical simulations are used alongside observational data to refine estimates of the star's mass, luminosity, and evolutionary stage. By inputting measurements from spectroscopy and astroseismology into computer models, scientists can simulate the star's history and predict its future, adding another layer of understanding to what would otherwise be just a faint point of light in the sky. The precision of these techniques is staggering. For Kepler 444, the age uncertainty is only about plus or minus 1 billion years, a small fraction compared to the star's 11 billion year lifespan. Similarly, the planet's radii are determined with incredible accuracy, revealing that they are remarkably similar in size to Earth and Venus. Such detailed knowledge about a star more than 117 light-years away is a testament to the power of modern astronomical techniques. What makes these methods particularly exciting is that they can be applied to other ancient stars as well. Every new star studied with spectroscopy, astroseismology, and transit observations contributes to a growing cosmic archaeological record, helping astronomers trace the history of the galaxy, the formation of planets, and the potential early conditions for life. Kepler 444 was a trailblazer in this sense. It demonstrated that ancient stars with compact planetary systems could be studied with remarkable precision, setting a standard for future research. Ultimately, the combination of spectroscopy, astroseismology, and the transit method transforms Kepler 444 from a distant speck of light into a fully characterized system, revealing not only its chemical composition and age but also the architecture and nature of its planets. These techniques are what allow us to study a star older than our solar system in such detail, bridging billions of years of cosmic history and providing a direct glimpse into the early Milky Way. The discovery of Kepler 444 and its 5 rocky planets generated a wave of scientific excitement precisely because it defied long-held expectations about the universe and planet formation. Before its discovery, astronomers generally believed that complex planetary systems, especially those with Earth-sized, rocky planets, were most likely to form around younger stars rich in metals. Heavy elements like iron, silicon, and magnesium are crucial for building terrestrial planets, and the early universe was metal-poor, composed primarily of hydrogen and helium. To find an ancient star over 11 billion years old with a fully formed planetary system was, in essence, like discovering a detailed blueprint of planetary formation in the universe's infancy. One of the first sources of astonishment came from the sheer age of the system. Kepler 444 formed only about 2.6 billion years after the Big Bang, a time when the universe was still in its formative stages. At that point, galaxies were still assembling, the Milky Way was relatively young, and heavy elements were scarce. The prevailing assumption was that rocky planets would be rare, if they existed at all, in such an environment. Yet Kepler 444 disproved this notion by hosting 5 fully formed, Earth-sized planets. This overturned the belief that planets, especially terrestrial ones, required chemically mature stars to form. Another element of excitement was the compact configuration of the planets. All 5 orbit very close to their star, with orbital periods ranging from 3.6 to 9.7 days. This extremely tight arrangement challenges existing models of planetary system stability. Astronomers were astonished not only that the planets existed but that they had remained in stable orbits for over 11 billion years. Conventional models predicted that such close-packed systems would be highly unstable over cosmic timescales, prone to gravitational perturbations that could eject planets or cause collisions. The Kepler 444 system demonstrated that ultra-compact planetary systems can survive for nearly the entire age of the galaxy, which was both surprising and inspiring for theorists. The planet's size and composition added to the intrigue. All 5 are small, rocky worlds similar in size to Earth and Venus. In a universe where early stars were metal-poor, conventional wisdom suggested that planets forming at this stage would be too small or too sparse to survive. Yet Kepler 444's planets are not only present, they are substantial, tightly packed, and remarkably resilient. This forced scientists to reconsider the relationship between stellar metallicity and planet formation, showing that rocky planets could form even in environments previously thought hostile to planet building. The discovery also had implications for the search for life. While Kepler 444's planets are too close to the star to be habitable, their very existence proves that rocky planets could form billions of years before Earth emerged. This opened up the tantalizing possibility that habitable planets, and potentially life, could have arisen elsewhere in the galaxy long before our solar system even existed. For astronomers and astrobiologists, the system essentially rewrote the timeline for planetary and potentially biological development in the Milky Way. From a technical perspective, the discovery also represented a triumph of observational astronomy. Detecting planets around such an ancient star, located over 117 light-years away, required extraordinary precision in both the Kepler Space Telescope's photometry and subsequent analysis using spectroscopy and astroseismology. Each planet's tiny transit across the star produced a minuscule dip in brightness, fractions of a percent, that had to be measured and verified across multiple observations. The fact that astronomers could extract such detailed information about the planet's sizes, orbits, and even their survival over billions of years was nothing short of groundbreaking. Beyond the data itself, the discovery of Kepler 444 sparked excitement because it challenged existing models of planetary formation. Traditional theories suggested that high metallicity was essential for forming terrestrial planets. Finding a metal-poor star with a fully realized planetary system demonstrated that these models were incomplete, prompting a re-evaluation of the factors necessary for planet formation and long-term survival. This means that rocky planets could be far more widespread across the galaxy than previously assumed, even around stars that formed early in the Milky Way's history. The discovery also ignited a sense of cosmic perspective. Kepler 444 is older than the Earth by more than 6.5 billion years, a reminder that our planet and solar system are relatively recent developments. In a universe that has been forming planets for most of its history, astronomers were thrilled not only by the technical achievement of observing such a distant, ancient system, but also by the philosophical implications. This star system provides a tangible link to the early epochs of the universe, giving humanity a direct connection to events that occurred billions of years before life on Earth even began. Finally, the scientific excitement surrounding Kepler 444 stems from the promise it holds for future research. By demonstrating that ancient, compact planetary systems exist, Kepler 444 has become a key target for upcoming telescopes like the James Webb Space Telescope and other next-generation observatories. Scientists are eager to study it in even greater detail to understand planetary composition, orbital dynamics, and the conditions under which planets can survive for billions of years. Each new observation promises to deepen our understanding of both planet formation and the broader evolution of the Milky Way. In short, astronomers were astonished because Kepler 444 is simultaneously ancient, compact, resilient, and full of rocky planets. It defied expectations, challenged theories, and provided a direct glimpse into a period of the universe when planet formation was only beginning. It is a rare cosmic treasure, combining both scientific value and philosophical significance, and it continues to inspire researchers to reconsider what is possible in the early universe. Kepler 444 represents a profound challenge to traditional models of planet formation because it directly contradicts a long-standing assumption that stars must be rich in heavy elements, or metals, to form rocky planets. For decades, astronomers believed that metallicity, the abundance of elements heavier than hydrogen and helium, was the key ingredient in planet formation. Metals like iron, silicon, magnesium, and oxygen are essential building blocks for terrestrial planets. Without them, conventional theory suggested, planet formation would be slow, inefficient, or even impossible. Kepler 444 appended that assumption. This star is metal-poor, meaning its composition contains significantly fewer heavy elements than our Sun. It formed over 11 billion years ago, at a time when only a few generations of massive stars had lived and died, enriching the interstellar medium with metals through supernova explosions. According to older models, a star forming in such an environment would be unlikely to produce rocky planets. At best, only tiny planetesimals, too small to survive or coalesce into a stable system. Yet Kepler 444 boasts 5 rocky, Earth-sized planets, tightly packed yet enduring for billions of years. This is not a marginal system. It is fully realized, with planets large enough and stable enough to exist over almost the entire lifetime of the galaxy. The existence of these planets indicates that rocky planet formation is more robust than previously believed. While heavy elements do aid the process, Kepler 444 shows that even in metal-poor conditions, protoplanetary disks can assemble solid planets. This forces theorists to revisit their models, considering mechanisms that allow planet formation in chemically sparse environments. For example, the process of planetesimal accretion may be more efficient than expected, or early disks may concentrate available metals into dense regions where planets can form. Either way, the star demonstrates that metallicity is not an absolute barrier to terrestrial planet formation. It influences abundance and size, but it does not preclude the existence of rocky worlds. Kepler 444 also challenges assumptions about the timescale of planet formation. Early models posited that in metal-poor environments, planet formation would be slow, perhaps preventing the assembly of planets before the protoplanetary disk dissipated. Yet the system's planets clearly formed early and solidified into stable orbits for billions of years. This indicates that planet formation processes are surprisingly rapid and resilient, even when the raw materials are scarce. The implication is profound. Terrestrial planets could have been forming across the galaxy long before Earth emerged, opening a far earlier window for the potential development of life. Another way Kepler 444 challenges old models is by demonstrating that compact systems can form in metal-poor environments. Traditional theories often assumed that dense, tightly packed planetary systems required abundant metals to build enough mass in the inner disk. However, Kepler 444's planets are all small and closely spaced, orbiting within a region smaller than Mercury's orbit. This suggests that early planetary systems could assemble in a variety of architectures, even with limited resources, challenging the idea that low metallicity stars can only host sparse or unstable planetary systems. The system also forces scientists to reconsider the relationship between stellar metallicity and planet type. Observations in the past suggested that metal-rich stars are more likely to host gas giants, while metal-poor stars might struggle to produce any planets at all. Kepler 444 complicates this narrative. It has no large gas giants, consistent with metal-poor predictions, but it has multiple small, rocky planets, proving that terrestrial planet formation does not strictly depend on high metallicity. This nuanced view reshapes the way astronomers think about planet demographics across the Milky Way. Kepler 444 has also influenced the broader field of planetary system evolution. Its compact, ancient system demonstrates that once planets form in a stable configuration, they can endure for billions of years, even in environments thought hostile to long-term survival. This challenges previous assumptions that planets in the early universe would be too fragile to persist or that early systems would be largely barren. It suggests that the universe may be teeming with rocky planets formed billions of years before our solar system, many of which could be stable enough to host life. From a theoretical standpoint, the star has sparked a re-evaluation of protoplanetary disk models. Scientists now investigate how metal-poor disks can efficiently gather the materials needed for rocky planets, what role disk density and dynamics play, and how migration and resonance patterns might stabilize these early systems. Kepler 444 acts as a real-world test case, forcing models to account for observations rather than assumptions, and showing that early planetary formation was more widespread, more resilient, and more versatile than previously believed. In essence, Kepler 444 is a cosmic counterexample, a star system that demonstrates the limits of prior assumptions and expands our understanding of how planets form. It proves that rocky worlds are not exclusive to metal-rich, young stars. They can emerge in ancient, metal-poor environments and survive for billions of years. Its discovery compels scientists to think creatively about planetary formation, system stability, and the early opportunities for life in the universe. In doing so, Kepler 444 reshapes the foundational theories of how planets come to exist. Kepler 444 stands as a remarkable cosmic survivor, a star system that has endured nearly the entire history of the Milky Way. At over 11 billion years old, it predates the formation of our Sun by more than 6.5 billion years and has persisted through countless cosmic events that might have destroyed lesser systems. Its resilience is a testament not only to the stability of its star but also to the architecture and endurance of its 5 tightly packed, rocky planets. The story of Kepler 444 is, in many ways, a story of survival against astronomical odds. To understand the magnitude of its resilience, consider the conditions under which Kepler 444 formed. The universe was young and dynamic, galaxies were still merging and evolving, and supernovae were frequent, scattering heavy elements and generating powerful shockwaves. In this chaotic environment, A fragile star system could easily have been disrupted, its planets stripped away, or its formation even prevented. Yet Kepler 444 emerged fully formed, with 5 planets already assembled in stable orbits around its star. This alone sets it apart from most planetary systems studied today, which tend to be younger and less resilient due to less extreme longevity. The planet's survival is particularly remarkable because they orbit very close to their star, all within a region smaller than Mercury's orbit around the Sun. Such proximity exposes them to intense stellar radiation, tidal forces, and gravitational interactions that can destabilize or even destroy planets over time. Despite these pressures, the Kepler 444 system has remained intact for more than 11 billion years, demonstrating a resilience that challenges prior assumptions about the fragility of tightly packed planetary systems. Its planets have endured cosmic radiation, potential nearby supernovae, and the subtle but relentless gravitational influences of other stars passing through the galaxy. The star itself contributes significantly to the system's longevity. As a K-type orange dwarf, Kepler 444 is smaller, cooler, and longer-lived than stars like our Sun. Its stable energy output and slow rate of stellar evolution have created a relatively calm environment for its planets, allowing them to orbit safely for billions of years. Whereas massive stars burn brightly and die young, potentially obliterating surrounding planets in supernovae, Kepler 444's steady, enduring presence has given its planets an extraordinary window of survival. Another factor in the system's resilience is the planet's orbital configuration. They orbit in a tightly packed, likely resonant pattern, which minimizes destructive gravitational interactions between them. This configuration is a delicate but enduring balance. Any slight shift could have destabilized the system. Yet the planets have maintained this harmony for billions of years, a cosmic choreography that has persisted almost since the beginning of the Milky Way itself. The Kepler 444 system has also survived galactic dynamics. Over billions of years, stars move within the galaxy, encountering tidal forces, passing near massive molecular clouds, and sometimes experiencing close encounters with other stars. Each of these interactions has the potential to perturb planetary orbits or even eject planets from their systems. Kepler 444's planets, however, have remained in stable orbits despite all of these potential disruptions, highlighting a level of endurance that is extraordinary even on cosmic timescales. The resilience of Kepler 444 also has implications for our understanding of planetary survival and habitability in the early universe. If rocky planets could endure for billions of years around an ancient star like Kepler 444, it suggests that other planets, including those in habitable zones around similar stars, may have survived long enough to allow life to develop. It demonstrates that planetary systems are not necessarily ephemeral. They can be remarkably persistent, enduring for nearly the entire age of the galaxy if conditions are right. From a broader perspective, Kepler 444's survival emphasizes the vastness of cosmic time. Humanity tends to think in lifespans of decades or centuries, even millennia, but this star system has endured. For more than 11 billion years, witnessing the birth and death of countless stars, the formation of the Milky Way spiral structure, and the eventual emergence of our Sun and solar system. It is a living archive of galactic history, a survivor that connects the present universe with its earliest epochs. In essence, Kepler 444 is a cosmic time capsule, its resilience offering a direct link to the early universe. Its survival challenges our notions of planetary fragility, expands the timeline for potential planetary habitability, and provides astronomers with a unique laboratory to study the long-term dynamics of stars and planets. It is both scientifically invaluable and philosophically inspiring, a reminder that some systems in the cosmos have endured virtually unchanged for the vast majority of the galaxy's existence. Kepler 444 is not merely old. It is enduring, a testament to the strength of planetary systems and the stability of stars capable of hosting planets over billions of years. It is a reminder that the universe preserves its earliest creations, and that these ancient survivors hold critical lessons about planet formation, system dynamics, and the potential for life across cosmic time. Its continued existence demonstrates that the cosmos is not only vast in space but also resilient in time, able to maintain intricate planetary systems over epochs far beyond human comprehension. The study of Kepler 444 has already expanded our understanding of ancient stars and their planetary systems, but future research with next-generation telescopes promises to unlock even deeper insights into these cosmic time capsules. The James Webb Space Telescope, JWST, along with upcoming ground-based observatories and space missions, offers the potential to study stars like Kepler 444 and their planets with unprecedented precision, revealing details that were previously beyond our reach. One of the key advantages of JWST is its sensitivity to infrared light, which is crucial for studying cooler, older stars like Kepler 444. Infrared observations can penetrate dust that may obscure the star in visible wavelengths and provide more accurate measurements of its temperature, luminosity, and stellar activity. This allows astronomers to refine models of the star's internal structure and evolution, yielding even more precise age estimates. For a star already over 11 billion years old, narrowing down its age with greater accuracy helps astronomers reconstruct the timeline of the early Milky Way and the formation of its first planetary systems. JWST also has the capability to study the atmospheres of exoplanets, a field that was largely inaccessible with earlier telescopes. While Kepler 444's 5 planets orbit extremely close to the star and are too hot to support life, JWST could detect atmospheric signatures, if any exist, such as remnants of primordial gases or exotic chemical compositions. Observing these atmospheres can provide insight into the processes that shaped planetary evolution in the early universe, including atmospheric retention, stellar radiation effects, and potential migration patterns. Even for inhospitable planets, this data is invaluable for understanding how planets survive and evolve over billions of years. Another avenue of research is high-resolution spectroscopy with JWST and future extremely large telescopes on Earth, such as the Extremely Large Telescope, ELT, in Chile. Spectroscopy allows scientists to measure the star's elemental abundances in finer detail than ever before. For Kepler 444, this means a more complete understanding of its metallicity, including trace elements that can hint at the conditions in the protoplanetary disk where its planets formed. Detailed chemical profiles help refine models of early planet formation and provide context for comparing other ancient stars in the galaxy. Future research also includes astroseismic studies at unprecedented precision. While Kepler and other missions have already provided valuable astroseismic data, upcoming missions and instruments can detect even more subtle stellar oscillations. This can improve estimates of stellar density, internal rotation, and age, and reveal the internal physics of ancient stars in ways that were previously impossible. For Kepler 444, this means understanding how an 11-billion-year-old star maintains stability and supports a planetary system over such immense timescales. In addition, JWST and next-generation instruments can help identify other ancient planetary systems similar to Kepler 444. By studying multiple metal-poor, ancient stars, astronomers can begin to understand how common these long-lived rocky systems are and whether Kepler 444 is an outlier or part of a broader population. This has major implications for galactic archaeology, as each ancient system provides a piece of the puzzle about the early history of the Milky Way and the formation of planets in low metallicity environments. The study of Kepler 444 with future technology also opens doors to testing theories of planet survival and orbital dynamics. Long-term monitoring of the system's planets may reveal subtle changes in their orbits, resonances, or interactions that shed light on how such a compact system has remained stable for over 11 billion years. Understanding these mechanisms is critical for building accurate models of planetary system evolution over cosmic timescales. Moreover, future research can explore the early chemical enrichment of the galaxy by comparing Kepler 444 with other ancient stars. By studying the elemental composition of multiple old stars and their planetary systems, astronomers can trace the accumulation of metals over time, investigate the role of early supernovae, and understand the conditions under which the first terrestrial planets formed. JWST's sensitivity and resolution make it uniquely suited for this kind of galactic archaeology. Finally, research into Kepler 444 and similar stars will continue to inform the search for life in the galaxy. While this particular system may be too hot for habitable planets, understanding how early rocky planets formed and survived helps constrain the conditions under which potentially habitable worlds could exist elsewhere. If rocky planets were forming billions of years before Earth, life could theoretically have emerged on other ancient worlds. JWST and future telescopes will help identify and characterize these systems, expanding our understanding of where and when life could exist in the universe. In summary, upcoming telescopes like JWST will allow astronomers to study Kepler 444 and its ancient planetary system in extraordinary detail. From precise measurements of the star's age and composition to atmospheric studies of its planets, future research will refine our understanding of early planet formation, system stability, and the early history of the Milky Way. Kepler 444 serves as a gateway to the distant past, and with a new generation of instruments, we are poised to unlock secrets that will illuminate not only this star but the entire early galaxy. Kepler 444 has profound implications for our understanding of the potential for life in the universe, reshaping long-held assumptions about both the timing and the environments in which life could emerge. Traditionally, scientists believed that life-supporting planets required stars rich in metals, forming relatively late in the galaxy's history. The discovery of Kepler 444, a metal-poor star over 11 billion years old with 5 rocky planets, forces a reconsideration of this narrative. It shows that rocky planets, the essential platform for life as we know it, could form much earlier than previously thought, dramatically extending the window of opportunity for life in the cosmos. One of the most important shifts in perspective comes from the timing of planet formation. Kepler 444 formed just 2.6 billion years after the Big Bang, and its planets likely coalesced shortly afterward. This means that terrestrial, potentially habitable worlds could have existed billions of years before Earth or the solar system formed. While the planets around Kepler 444 itself are too close to the star to support life, their very existence proves that rocky planets were already forming early in the galaxy's history, and it is reasonable to assume that similar systems with planets in temperate zones may have existed as well. The implication is profound. The universe could have hosted habitable environments long before our Sun ignited. Kepler 444 also reshapes our understanding of where life could arise. Metal-poor stars were previously considered unlikely hosts for planets because the elements needed to form solid surfaces were scarce. Yet Kepler 444 demonstrates that planet formation does not require high metallicity. This means that habitable planets might exist, or have existed, around other ancient, metal-poor stars in the galaxy. Life, therefore, may not be confined to younger, metal-rich stars like the Sun. It could potentially emerge around a much broader range of stellar environments, including the earliest generations of stars. Another aspect of its broader significance lies in planetary longevity and stability. The planets around Kepler 444 have survived in tightly packed orbits for over 11 billion years. This demonstrates that planetary systems can endure for most of the universe's history, providing stable environments long enough for life to potentially develop. In other words, the longevity of these planets suggests that the earliest habitable worlds could have had billions of years for biological evolution, far exceeding the timescale life has existed on Earth. This challenges the notion that habitable conditions are rare or limited to recent cosmic epochs. Furthermore, Kepler 444 has implications for the distribution of potentially habitable planets in the Milky Way. If compact, rocky planetary systems can form and survive around ancient stars, it is likely that similar systems exist, or existed, throughout the galaxy. The discovery encourages astronomers to broaden their search beyond Sun-like stars, including ancient, metal-poor stars that were previously considered unlikely candidates. By expanding the types of stars considered capable of hosting rocky planets, Kepler 444 effectively increases the potential habitats for life across the galaxy. From a philosophical perspective, the system forces us to reconsider our place in cosmic history. Earth and our solar system are relatively young, forming over 6.5 billion years after Kepler 444. If life could have emerged on earlier planets, then civilizations, ecosystems, or even advanced life forms could have existed long before humanity, potentially for billions of years. The discovery of such an ancient planetary system expands the temporal horizon for life in the universe, suggesting that humanity may be newcomers to a cosmos where life had a head start on us. Kepler 444 also influences our understanding of the universality of planet formation. The system demonstrates that rocky planets are not rare anomalies but may be a common feature of stars across a wide range of ages and metallicities. If planets could form in the early universe around metal-poor stars, it implies that rocky worlds, and by extension, the potential for life, could be far more abundant than previously assumed. This challenges older models of planetary demographics and encourages a re-evaluation of how many planets in the Milky Way may have existed long before Earth. In practical terms, the broader significance of Kepler 444 also guides future exploration and observation strategies. Telescopes like the James Webb Space Telescope, alongside ground-based observatories, can now target ancient, metal-poor stars to search for rocky planets, investigate their atmospheres, and assess their potential for habitability. This focus broadens the scope of astrobiology, pushing the frontier from merely identifying exoplanets around sun-like stars to understanding the history of potentially habitable environments throughout cosmic time. Finally, the system reshapes our conceptual framework for life's emergence. It demonstrates that the conditions necessary for rocky planets, and therefore for life, were present far earlier than the formation of our solar system. Even if life did not arise around Kepler 444 itself, its planets prove that early cosmic environments were capable of supporting terrestrial worlds. This realization encourages scientists to think on a galactic timescale, considering billions of years as the arena in which life could appear, rather than the narrow window defined by Earth's relatively young age. In short, Kepler 444 is a game-changer in our understanding of habitability. It extends the timeline for rocky planet formation to nearly the beginning of the galaxy, demonstrates that low metallicity stars can host enduring planets, and suggests that the universe may have been capable of supporting life billions of years before Earth. By expanding both the temporal and spatial horizons for habitability, this ancient system fundamentally reshapes how scientists approach the search for life in the cosmos. Reflecting on Kepler 444 invites us to confront the immensity of cosmic time in a way that is difficult to grasp. Over 11 billion years have passed since this star formed, a span nearly 3 times longer than the age of the Earth. In human terms, it is almost inconceivable. Our entire recorded history, our civilizations, and even the existence of our species are but fleeting moments in comparison. Kepler 444 provides a tangible connection to an era when the universe was still young, galaxies were forming, and the first rocky planets were taking shape. It is a window into a past so distant that Earth, the solar system, and all life we know had yet to exist. When we consider the longevity of this star and its planetary system, we realize that the universe is not only vast in space, but overwhelmingly vast in time. Kepler 444 has witnessed epochs that spanned billions of years, surviving the dynamic evolution of the Milky Way, from early galactic mergers to the settling of the spiral arms we see today. Its planets have endured all of this, orbiting in a remarkably stable configuration. This endurance offers perspective. While human life and even our entire civilization are transitory, the cosmos operates on timescales that dwarf our existence. Kepler 444 also highlights the ancient roots of the galaxy. By studying such stars, astronomers perform a kind of cosmic archaeology, piecing together the history of the Milky Way, understanding how the earliest stars and planets formed, and how the galaxy chemically evolved over time. Each data point from Kepler 444 is a story from a chapter billions of years old, a direct message from the early universe preserved in the star's light and the enduring stability of its planets. In this way, the star serves as a bridge across cosmic epochs, linking the present moment to a universe that existed long before the Sun or Earth appeared. Contemplating Kepler 444 encourages a profound sense of humility and wonder. Our solar system, ancient as it feels to us, is in fact a relatively recent participant in the Milky Way's history. The existence of stars like Kepler 444 reminds us that the universe is filled with survivors of epochs far older than our own. It prompts us to reflect on our place within this vast continuum of time. We are part of a young generation of planetary systems and civilizations, observing a cosmos that has already endured billions of years of history. The star also stirs philosophical and scientific curiosity about life in the early universe. If rocky planets could form and survive around a metal-poor star so long ago, could life have arisen elsewhere long before Earth? Could civilizations, or at least biological processes, have existed billions of years prior to our solar system? These questions deepen our appreciation of the universe's potential and complexity, illustrating how ancient systems like Kepler 444 expand not just our knowledge, but our imagination. Finally, Kepler 444 is a reminder of the continuity of cosmic processes. Stars are born, planets form, and galaxies evolve, and yet some systems endure virtually unchanged for most of the universe's lifetime. Observing this star allows us to see the Milky Way as it was in its youth, connecting us to a time when the first solid worlds were forming. It is a humbling and awe-inspiring experience, realizing that the cosmos is far older and larger than any single human perspective, yet through observation, we can trace a thread of continuity across billions of years. In short, Kepler 444 encourages us to reflect on both the scale of time and the connectedness of the universe. It is a star that existed long before Earth, hosting planets that have persisted across nearly the entire history of the Milky Way. Through it, we gain perspective on the fleeting nature of human existence, the endurance of cosmic systems, and the vast stretches of time over which the universe has been creating, shaping, and preserving planets. It is a living relic of the early cosmos, bridging the immense gulf between the distant past and our present understanding of the universe. Kepler 444 is nothing short of a living fossil of the cosmos, a star system that has persisted almost unchanged for more than 11 billion years. Its existence is a humbling reminder of just how small and young our own solar system is in comparison. While we often regard Earth and the Sun as ancient and enduring, they are in fact newcomers on a cosmic stage that has been active for billions of years before our solar system ever formed. Kepler 444, with its 5 rocky planets orbiting steadily around a stable, metal-poor star, serves as a monument to the resilience and longevity of planetary systems, a relic of an epoch when the universe was still in its formative stages. The awe inspired by Kepler 444 comes not only from its age but from its survival and structure. It demonstrates that planet formation began incredibly early in the universe, proving that rocky worlds could exist billions of years before Earth appeared. Its planets, although too close to the star to support life, offer concrete proof that the building blocks for life, solid terrestrial planets, were present almost immediately after the galaxy began producing stars. In essence, Kepler 444 shows us that the universe has been creating the conditions for life long before our solar system existed, pushing back the timeline for planetary evolution and the potential for biological processes by billions of years. When we compare Kepler 444 to our Sun, the contrast is striking. The Sun, a relatively young star at about 4.6 billion years old, is less than half the age of Kepler 444. Earth, likewise, formed billions of years after these ancient worlds were already orbiting their star, enduring the slow passage of cosmic history. This comparison highlights the ephemeral nature of our own existence in the grand narrative of the galaxy. Kepler 444 is a vivid reminder that while we may perceive our solar system as ancient and permanent, it is, in cosmic terms, remarkably young, a newcomer amid a galaxy filled with ancient stars and planets. Kepler 444 also inspires, or because it challenges our understanding of what is possible in the universe. Its metal-poor composition and compact planetary system contradict the long-held belief that Earth-sized planets could only form around metal-rich stars. Its survival over 11 billion years defies expectations about the stability of tightly packed planetary systems. And yet, here it stands, a fully realized system, enduring for nearly the entire lifetime of the galaxy. The star and its planets are a testament to the tenacity of cosmic structures, offering a glimpse into the enduring processes that govern the universe. From a philosophical standpoint, Kepler 444 connects us to the ancient past of the cosmos. It allows us to imagine a galaxy that existed billions of years before the Earth, filled with stars and planets that may have already hosted the raw ingredients for life. It encourages reflection on the vastness of time and space, on the longevity of planetary systems, and on humanity's small yet conscious place within this immense universe. By studying stars like Kepler 444, we are not just exploring distant points of light, we are connecting with the early universe itself, witnessing the survival and evolution of a system that has endured the full sweep of galactic history. Ultimately, Kepler 444 is a cosmic time capsule, a reminder that the universe has been forming stars and planets for most of its 13.8 billion year history. It underscores the fact that our solar system is a relatively late addition to this ongoing story. By observing it, we gain perspective on both the endurance of celestial systems and the youthfulness of our own planetary neighborhood. It is a star system that carries within it the story of the early Milky Way, offering insight into the first generations of planets and the potential for life in the ancient universe. In closing, Kepler 444 invites us to look up with awe and humility. It reminds us that the cosmos is vast, ancient, and filled with resilient structures that have persisted for billions of years. Our solar system, impressive as it may seem from a human perspective, is merely a young participant in a much older and more enduring universe. Kepler 444 is a living testament to the longevity and perseverance of stars and planets, a fossil of cosmic history that connects us directly to the early epochs of the Milky Way and to the universe as it was nearly at the dawn of time. Its existence is both inspiring and humbling, reminding us of the enduring processes that shape the cosmos and our place within it. Kepler 444 is not just an old star. It is a symbol of the universe's resilience, creativity, and continuity, a window into a distant past, and a mirror that reflects the youth and relative fragility of our own solar system. Its story encourages us to marvel at the cosmos, to appreciate the vast stretches of time over which planets and stars endure, and to recognize that even the youngest members of the galaxy, like our Sun and Earth, are part of a much larger, ancient narrative. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.